All right. All right. So we're gonna incorporate electrical into engine performance, and the reason for that is a lot of the stuff that we're gonna do. Let's say when we get into checking sensors, it's pretty much electrical work. Or when we get into doing ignition, that's pretty much electrical work. When you get into fuel, it could be electrical or it could be mechanical. So like we could check a fuel pressure with a gauge, that's all mechanical. But if we get into like troubleshooting a pump or injectors, it's all electrical, right? So a big part of engine performance is going to be electrical. So some of you have taken electrical, good. Some of you are taking it now, good. Some of you haven't taken it at all. I'm going to do the best I can to get you kind of up to speed, but also just know there's like a whole, if you wanted, there's a whole 10 units of electrical videos that I've got if you want to self-study and be ready for this. In the order of how I would pursue these tests, I would absolutely do A6 first. I wouldn't try to do A8 until you've done A6, and A6 is electrical. So I would do it like that. And I would also do engine repair as well, A1. So we did some of that last week. Some of that was kind of like overlap with engine work, or a couple weeks ago. This is going to be some overlap with A6. Okay, so we'll jump in there. Now, if you look, here's a summary. This is something you've seen when we did the onboard diagnostics and the computerization. So right here, you've got our ECM, that being kind of the brain of the system. Then over here, you've got a bunch of inputs, right? So if we have, let's say a problem, for example, now that you guys know inputs decent, let's say we pick a sensor, maybe throttle position. The ECM needs to know the throttle position to know what to do, right? So if we have a throttle position sensor, that's most likely going to be a variable resistor. If we had a problem with that variable resistor, we may get a code. A lot of times we would. Sometimes we wouldn't. But if we thought it was an issue with the throttle position sensor, we could see that with the scan tool, view it, check the code, look at the live data, see if the percentage is right. But after that, we got to resort to most likely a meter, or we might even use a picoscope. So you pretty much look at this in a diagram and you see what's going on with the circuit. So like a typical variable resistor is going to be like 3 wires. We need to make sure it has the correct voltage on each of the wires to determine, is it the sensor, is it the wiring, or is it the module, right? And so that's going to be like a repetitive term. You get a code for the throttle position sensor. It could be the sensor, it could be the wiring, it could be the ECM. And then, like I shared with you, I think it was 2 weeks ago, there's always other exceptions where it could actually be a programming issue, and there might be a TSB related to it and stuff like that. So do your due diligence. If you got a code related to this or a problem, look for TSBs, see if there happens to be a software update. But if there isn't, which is sometimes, then we got to be able to troubleshoot that. Now, the way we troubleshoot a variable resistor is different than a switch. We could use the same tools, or we could use different tools. Or an AC frequency or a DC frequency sensor. Those are really similar, but if you're trying to test an AC frequency sensor with your meter and you have it set to DC, you're not going to be able to test it. You're going to get weird numbers. You're going to be confused, and you're going to go to like a senior tech or a foreman or something and just say, I don't understand what the heck is going on and how and why and et cetera. Right? So when we get into this stuff, there's a lot to know. So right now is going to be the electrical overview of this. And then as we get into sensors, we may cover how to check that sensor specifically. We'll do a little bit today, but this is not a conclusive list of all the sensors. There could be 50 sensors on the engine control side. So there's a lot. All right. And then the ECM, that can have its own electrical tests as well. So like, for example, this ECM to work is not so different than the computer that's right here. It needs power, you may say, right? So that this computer is not going to work if it's not plugged into the wall, correct? So over here, I found this cheat sheet. Remember how I keep saying that the settings on the screen are weird on this computer? Well, I realized I think that somebody uses this room more regularly than us, like someone probably in STEM, science, technology, engineering, and math. That's what this building is. And every time I come in, they have it set to duplicate, and I come in and I change it to extend because I want one screen over here and I want one screen over here that are different so I can see different things. And I think somebody's been getting really tripped up on that, because if you look right here, I've got this guide to how to set it, to how to control the displays. So like for me, I have more of a troubleshooting brain. That's going to have to be all you. You're going to want to know, how does something work? What do I do? What do I try? How do I fix it? How do I adjust it? But I've had a lot of experience with people more on the academic side, and it may be science, technology, engineering, and math. But based on some things I saw over here, remember there were some cells drawn. There was like, they're teaching students about ribonucleic acids, and these types of things. Well, I'm gonna bet, this may be slander, but it probably isn't, they can teach you all about the powerhouse of the cell and the DNA, but they can't understand how to switch this computer back to extend rather than duplicate, right? So a lot of times, people don't have that troubleshooting brain where it's like, how do I figure it out? So there's been numerous occasions, because I like to talk with the people in IT at the schools, because we're similar, right? Car comes in, it's messed up. Sometimes it's something really dumb and the customer just didn't know. The one thing that they would get is, the computer doesn't work, call IT. Hey, the computer doesn't work. It's not plugged in. It's kind of the same as this, right? This ECM is not going to work if it's not plugged in. But the thing is, like with a computer like this, you plug it into the wall like that, and that's a little, it's like a 2-prong or a 3-prong outlet and a receptacle, and you could pull that out pretty easy. Well, these, you can't pull them out that easy. This is going to be a more secured harness. It's going to be clipped in better. But the reason the computer doesn't work when it's not plugged in is because it doesn't have power. We'll say power, okay? Now this computer runs on AC, so that's actually going to be like a hot and a neutral. But on this one, it needs to have 12 volts. It needs to have good ground. If your computer is not working, you may be like, oh, it's a computer. But then it's like, wait a minute. Now you sound like the people who are teaching biology, who are saying like, IT, the computer doesn't work, come help. They didn't see if it was plugged in, right? Like you got to start with some sort of basic understanding of how this thing works. Yes, it needs power. It needs 12 volts and ground. Okay, makes sense. So we are going to cover how to do some basic ECM diagnosis through electrical as well. And then on the other side, if you'll recall, there's outputs, right? So outputs do actions. So if we wanted to test a relay, there's some good ways to test a relay. What's kind of cool about this one is that's really just straight up A6 electrical material. It's not even engine performance specific. But the cool thing is, on the A8, they'll throw like a basic diagram showing a fuel pump and be like, the fuel pump doesn't work. And then they'll show you some different voltages. So it doesn't really matter if it's a headlight relay or a fuel pump relay. The way we're going to diagnose it's going to be the same. Obviously, if we have a problem with a headlight relay, the headlights don't work. But if we have a problem with the fuel pump relay, what do you think don't work? Exactly, which would cause a crank but no start. A shana na 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 na. Right? Exactly. There's the engine's turning over, the starter's moving, the flywheel, but if there's no fuel, there's going to be no combustion, right? So a lot of times, if you really like distill it down, a lot of the A8 material is just A6 applied to something specific, such as a fuel pump relay. Or we could have a motor, a solenoid, even a light bulb. So light bulb, if you did A6, like you'll be all over the light bulb, right? But if I were to cross off the light bulb and throw a motor in there, you'd be like, oh, I don't know. It's the same. The way we diagnose it is going to be the same. The motor needs 12 volts in ground to run, so we can check 12 volts in ground, right? So if your ECM is not commanding your motor, maybe there's a problem in here. If your ECM is commanding it, but the signal is not making it, maybe there's a problem in the wiring. If the ECM is commanding it successfully and the wiring is good, it might just be that you have a bad motor, right? So again, it's going to be I'm going to make it as simple as I can. It's either like let's say you got a problem with the sensor. It's either the sensor, the wiring, or the ECM. Let's say you got a problem with the motor. It's either the motor, the wiring, or the ECM. See, so it's like diagnosing the same, but on the other side. The motor doesn't give a signal. It receives a signal and does work. Cool. So that's kind of where we're going. Now we talked about if I was going to pick on the biology instructor who calls IT to make sure the computer's plugged in rather than just check it themselves. This is kind of the joke right here. But when we look at a diagram, there's a little more going on than just make sure it's plugged in. Cool. But if you think about it in that way, it'd be like, hey, that I can't communicate with that ECM in this case. It could be a PCM. And for the record, it could be any other module. It could be a body control module, a brake and traction control module. It could be whatever, 4x4, whatever you want. This lesson is going to be the same. All right, so if we take a look at this module, this is the ECM. This would be a diagram showing you all of what that ECM needs to boot up, right? So if you go in and you can't communicate with it and that ECM is not giving a signal to the injectors and to the coils, it's not going to run. But here's what the ECM needs. If you look right on top, what do you guys think BAT means? BAT. Yeah, so that's going to be battery voltage. If you look, where does it come from? It comes from the battery. That's why it's battery voltage. It goes up to the ignition switch. It goes up through a fuse. This is actually probably a fusible link. It breaks off and goes to the ignition switch. But see, we're not worried about that because it broke off before the switch. So that means it's going up this way through the EFI fuse and up into the battery. When is that ECM getting voltage then? When the key's on or off? Or all the time. That's the answer. Because look, when the key is on, that's what you're opening and closing in the ignition switch. But see, this one goes directly to that. It goes around the ignition switch. It doesn't need the ignition switch to be on or off. So when you see something that says BAT or B plus, and sometimes they'll even say B plus 1, you saw this picture before, that means that should have source voltage all the time. Engine on, engine off, key on, key off, key in the back seat, key at the customer's house. It doesn't matter. It should have source voltage. Now, what do you think the source voltage is? This is the source. Yeah, we could call it 12. I'm going to call it 12 all throughout this presentation. But technically, though, if a battery's fully charged, it's more like 12.6. Yeah, and if the battery's a little discharged, 12.5, 12.4, 12.3, 12.2. If the battery's pretty much dead, 11 point something, right? So you're not over here just looking for like 12.0. You really wouldn't want to start and check the battery voltage itself. And then whatever the battery voltage is, you should get essentially battery voltage. Now you might have it down like a 0.1 volt or even potentially 0.2 volts. But being that this doesn't go through any switches, it shouldn't really be dropping much more than like a 0.2 volts. So if you've got 12.6 here and you've got 12.5 here, 12.5 here, 12.5 here, all those check out. Make sense? What if we had 0, 0, and 0? You think that ECM is going to work? No. So you want to put a new ECM in it? You can. It's not going to fix anything. That's like if this computer isn't getting power from the outlet because the breaker's blown, you can put a new computer in there. You can put another new computer in there. You can put another new computer. Then you better call IT. And if you call IT and IT is putting multiple computers in there and they don't realize that the breaker's tripped, like somebody's getting fired. You know what I'm saying? So this is going to be you. You are going to be the equivalent of IT. So if you look at that, how are you going to check those though? Like that could be kind of hard. So there's a harness and the harness goes to the ECM and these aren't labeled and they might be red or they might be yellow or they might be some other color. I don't really know what color they are, but we'd have to get more into the wiring diagram, which we will. And you'd have to see what terminal is this. Let's just say that's terminal number 1, number 2, and number 3. You'd locate those and you'd actually prepare to do like a back probe, right? So when we get a little bit later, it's going to show back probing. When we go to back probe, that's actually how you're checking it. It's not quite as simple as like looking at it or anything like that. So we're going to actually use our meter and you could put the black lead on the ground and put the red lead on the BATT terminal number 1 carefully by back probing. That's easier said than done. And make sure that it's actually got the correct source voltage. So it's, when you explain it this way, let's say to some warranty administrator or something, they're like, oh yeah, they just checked to make sure that it had voltage on terminal 1, 2, and 3. But it's like, yeah, but what I really did was I looked into it, I looked up the wiring diagram, I found which terminals BAT B plus and B plus 1 were. I put them on a basically like a little a diagram to determine where they are, and then I had to disassemble the connector somewhat, and then I had to really carefully get in there and back probe. Like this may take you a half an hour just to see if it's got the voltage right there. Okay, and then guess what? You're not done, because after that, this one actually we're going to skip. Let's get down here to IGSW. What do you think that stands for? Ignition switch. Exactly. So when you think that should get source voltage based on this diagram? When it's switched. Exactly. So you'd be like, key off, IG switch should be 0 volts. Key on, it should be source voltage, right? So that might take you a little bit more time, because the thing is, you don't automatically know where these are. You got to look at them on the connector end view and see where the location is. So it's terminal 1, 2, 3, 5. Then you're like, all right, all the positives, all the powers are good. So if you ever hear somebody say, like, did you check all the powers to the ECM? And they're like, yeah, but did they really? Because I'm looking at terminal 1, terminal 2, terminal 3, and terminal 5, and that's going to take some time, and I wouldn't expect you to be able to do it in under a half an hour, especially starting out. So it's going to take some time. A lot of people will be like, yeah, I checked it, but they didn't. If you didn't check it and you assume it's the ECM and you throw ECM in there, that's hundreds of dollars, potentially 1,000 plus. And you might do that for this EFI fuse. You know, like, that's crazy. You know, maybe that EFI fuse blew because, I don't know, some mouse chewed some wire right here and shorted it to ground, and then you're putting an ECM in it, and it's not the ECM at all, right? So what we do here is going to be really critical. That's how you do diagnosis. You don't just, I mean, you can do whatever you want. I'm just letting you know, though, if you get hauled into court and they're like, hey, why'd you replace that? And you're just like, well, I mean, the ECM didn't power up, so I replaced it. See, if they try to put you under a microscope in court and they're like, you know, we're going to bring in a specialist who's going to testify against you. There's people much smarter than me with more qualifications than me. And if you say you put in an ECM because it didn't power up, they're all going to know that you check terminal 1, terminal 2, terminal 3, and terminal 5. And if you can't very clearly explain how that was a yes, you're wrong. You did it wrong. That's a fail. That's a straight to jail. Probably not to jail, but you're going to have to refund that customer's money or something. Okay, makes sense. So I'm showing you that. As we go down, if you look right here, this is kind of weird. There's E2 and E1. These are funny. If you look at this diagram, E2 goes to the sensors. E2 is not a ground for the ECU. It's a ground that the ECU provides. And this is just one example, by the way. So these terms are one specific. Every ECU, however, is going to give ground to the sensors. But to give ground, it's kind of like this. It's kind of like this. You know somebody who's miserable? You all do. Can a person who's really miserable ever actually be nice? They can't give what they don't have. You understand? They can't give what they don't have. The ECU can't give a ground if it don't have a ground. So this one, E1, is the ground that the ECU gets, right? The E1 provides ground for the ECU. Then the ECU provides ground to the sensors, right? So if you have a bunch of sensors that don't have a ground, it may very well be because the ECU doesn't have the ground at E1, right? So that's another thing you must check. Just to get that ECM to boot up, you need source, and a good ground, a healthy ground. And a lot of times they'll talk about how much voltage should drop. You really should not be dropping more than 0.2 volts on this ground right here. And so if you were to look up voltage drop and you were to put your black lead on the most negative and your red lead on the closer to positive, which sounds crazy because it's not positive, but it is, you shouldn't be dropping more than 0.2 volts right here. If you're dropping like 0.7 volts, that ground is, there's something wrong with that ground. Now, it could be the actual ground to the chassis, like an eyelet or a corrosion or something. It could also be the wire. It could also be the connector, like the terminal at the ECU. But anything over 0.2 volts is going to be a fail. Once in a while, I see numbers like potentially 0.5 volts, but 0.5 is usually when there's a switch involved. This with no switch is really going to be like a 0.2. 0.1 would be good. 0.2 would be acceptable. 0.3, 4, and 5 are like kind of sus, as you'd say. That's like kind of like, I don't know, right? Because if you have voltage drop on this ground becomes a load in the circuit, which means all these sensors aren't going to get the correct ground, right? They're going to get kind of like a ground with some corrosion on it. So that ground's critical. That, if you look at 1, 2, 3, 5, and E1, so that would be 7. That right there is what your ECU needs to power up, and that's it. And what this one doesn't show, because we weren't really talking about the electrical part, but I will say this computer is connected to the internet, right? So if I go to diagnose this computer remotely with my scan tool, my laptop, or whatever, and I can't communicate to that computer, now I'm going to say, like, if I can't communicate to that computer, but I can communicate to other computers in other buildings, there's something wrong with that computer. Cool. So I might go and be like, hey, is this computer powered up? And if I have 12 volts in ground and everything's chilling, I'll be like, this computer's powered up, but why can't I communicate on the network? What do you think might be causing me to not be able to communicate with it on the network, even if it's powered up? Something on the network. Exactly. So like in a car, that's usually going to be CAN. On a newer car. On the older car, it would be other things. In computer terms like this thing is not plugged into Ethernet. If it's not plugged into the internet, you can't communicate with it, right? So this is focused on the 12 volts in ground, but just so you all know, if your ECM, which it will also have communication lines. That's a different part of the diagnosis. So I just want to bring it up. You're not done if it's got the 12 volts in the ground. You also have to make sure it has a connection to the network, which is like the Ethernet cable. You know, I don't remember if it's yellow or blue. It depends on where it's at, right? But you know, the little cable you used to plug in? This is like different than Wi-Fi. Make sense? None of these ECMs and ECUs really work on Wi-Fi. Now, there's some stuff they do wirelessly, but this is not really a Wi-Fi computer. But basically, it'd almost be like if this computer wasn't on the Wi-Fi, you know, you wouldn't be able to communicate with it, right? So you got to check, is it on the Wi-Fi? Except there is none. There's hardwire two terminals, CAN high and CAN low. We got to check those too. When we get into networking, okay, that's later. Cool. Okay, so we kind of understand that so far. Now, from there, additionally, what we're going to do is, this is where it gets kind of complicated, but it's not horribly complicated. What's kind of funny is we've got 12 volts going here and here and here, but only if this relay right here is closed. This is the contactor side of the relay. So this would be like your control, your coil side. And this would be like the switch side, right? That's only got 12 volts if this EFI main relay right here is energized. So if this side has ground, how would we energize the EFI main? Can you tell? The EFI main, to energize this, all right, let's say this is a light bulb. How would we make the light bulb light up? You got ground on the left side. What do we need to give it on the right side? Yeah, let's give it 12 volts. Okay, so here's what happened. This is pretty interesting. If you look at this right off the baseline, we really only give 12 volts actually to battery. Then battery is going to be enough to power this up. Okay, and then when you turn the key on, this is going to get a signal from ignition switch. And then it's going to say like, oh, they just turned the ignition switch on. Now what I'll do is I'll send out 12 volts, which will magnetize this relay coil, which will pull this switch over, which will then actually give B plus and B plus 1. All right, so the circuit's just a little bit more complicated than I explained the first time, but it's not really a super big deal. But what if we had a problem with this EFI main relay? We would get 12 volts on bat, and then we may get 0 volts on B plus and 0 volts on B plus 1. And you'd be like, how the heck can that be? Or whatever. They're wired the same. Well, are they though? Because look, this breaks off before the relay and goes to bat. B plus and B plus 1 are after the relay. So if this relay is not getting magnetized, or if this relay has corrosion on the switch, that would actually explain both of those two being at 0. So it's really a matter of looking at the circuit, understanding the circuit, and then determining what the cause would be if a certain thing was defective, right? And so if it was the car, you'd probably be following some sort of a troubleshooting tree like we saw a couple weeks ago, or so I think it was last week, or if there's nothing really to hand guide you by the hand, like hold your hand, you're going to look at the wiring diagram like this, and you might have to study it a little bit and actually like trace it. And that's why I think it's so critical to cover this from a perspective of A6 for now, because there's a lot of questions and a lot of symptoms and concerns in broken cars that are just straight up electrical problems. So if this relay has an issue, you know, it needs ground here, it needs 12 volts here, it's going to have 12 volts here, and it's going to pass through the switch only when this is magnetized here. So that's your typical relay, right? And then we got one more interesting thing right here. You know, remember how I skipped that one? Now you know why. We got right here. What do you think to mill means? To mill. Yeah, exactly. So the ECM can send voltage out to the mill to light the check engine light. Makes sense? So if there's an error, the ECM will power that light bulb. So the mill is an output, right? So that's a big overview. Like one clue about that would be if you went to start the car and there was no check engine light, you know, when you turn the key on, the check engine light comes on for a bulb check and then turns off. If you don't have any bulb check at all, no nothing, you might actually look into like, hey, is the ECM even powering up? If it's not, if the car won't run and there's no check engine light, just know the ECM powers that check engine light. So if your ECM doesn't have all the correct voltage and ground, it's probably not gonna be able to power that check engine light. It's a clue. All right, now about electrical. Let's see if you guys can recall some things who were with me last semester. Voltage is like electrical pressure, right? So that's the push. That's the amount of pushing force. Like you can see here is a pretty good representation. I got one more that's fun that you can get a tattoo of if you want. But this one wouldn't be a good tattoo. This is a lame tattoo. The other one's a cool tattoo. Okay, so the electrical pressure is the voltage. The electrons are trying to flow based on the voltage, but what's slowing them down? The amount of resistance, right? And then depending on how much voltage and how much resistance you have, the result will be the amount of current flow. So like, again, I like to look at it kind of as water. If you have very little water pressure, you're not going to have a lot of volume of flow, right? But if you increase the water pressure, you're going to have a lot of flow. Partially why that's so critical is, let's say that we have a battery that's not fully charged. You think this system's going to power up right and work well? I don't think so. But if we were to back that up and remind you about the charging system, once the car's running, really all that power is coming from the alternator, right? So if you have a battery that's messed up, its main job is to get it started. Then the alternator's job is to keep the voltage high. So if it's you know, key on, engine off, you're probably 12.6 or maybe less, just a little bit less. Then once it's running, you're over 13. You're maybe 13.5, 13.8, 13.9, right? So the alternator provides that 13 point something. So technically, when your engine is off, you have less source voltage. And technically, when it's running, you have more source voltage now, right? Because the alternator's brought up the whole system voltage, okay? I want you to keep that in mind because I'm going to point a couple things out a little bit later. All right, but your battery also has to stabilize the system. So your alternator is really good at giving that power, but it can be kind of rough. Like if you rev it up, it might be up, and if you let it fall down, it might be down. And also, depending on the speed of your belt, which is based on engine RPM, you know, that voltage could be kind of like a little, I don't know, just a little rough, a little choppy. So you know what we do? What if you play a YouTube video and it's kind of choppy and it's like, shouldn't we buffer it a little bit? You want buffer it? You know, you like that one, huh? You want buffer it. The battery buffers. So if your alternator's charging at 13.7, 14, 13.8, 13.9, 13.7, the battery is going to actually kind of stabilize and buffer that and make it more like a 13.8 smooth. Okay. So if you do have a totally bad battery or a battery that's kind of like, you know, on the verge of failing, it can cause all sorts of electrical problems with this. All right. So if you get one code for the throttle position sensor, I'm not real overly concerned about the battery. But if you've got a whole bunch of sensor codes, a bunch of random codes and random problems, I might take a serious look at the battery, because if the battery's not buffering properly, it's going to be kind of like affecting all these different sensors. Kind of make sense? Now, if you go on the forums, every time there's any electrical problem, somebody has to chime and be like, hey, check the battery. It could be the battery. It's probably the battery. Change your battery. Do the battery. Check your battery terminals. Like, that's based in a little kernel of truth where, yes, the battery is the source of the power, but like the battery is not the problem all the time. So if you go on the forums, they blame the battery for everything. If you got an isolated issue with one particular circuit, it's not going to be the battery. If you got a bunch of random weird stuff that could all have the battery in common, maybe. Cool. All right. So if you look at that, that's the force, right? So our amperage is going to be higher. Our current's going to be higher with more voltage, or lower with less voltage. Now, if you look at resistance, and this is the one where we're going to spend more time, because your voltage is generally pretty consistent, but resistance is going to be a big issue. If you have excessive resistance, that's going to really drop your current flow, and it's going to make, for example, maybe your ECM is not going to get the correct amount of voltage and current to power up, or it's going to have a big voltage drop on the ground, or it's going to make a sensor read incorrectly. Resistance is a big problem all throughout the system. Make sense? So like if we look at the wires, if you have a nice big wire, well, let's say that this is length. If you have a long wire, that's going to give more resistance, and a short wire is going to give less. So like typically when the car's manufactured, they know how long the wires are going to be. So if you ever do a repair, you don't want to make that repair like overly long. Like I'll tap in right here and I got a 30-foot bundle of wire, but I don't feel like cutting it. So I'll just like make a few loops and zip tie it together and then run it there. Like you just added resistance into the circuit. Like you can't do that. If it's a light bulb, maybe it might glow a little dim, but if it's a sensor, that voltage is critical, and that's all a part of how the circuit works, right? So when we are doing these wiring repairs and tests and stuff, it all needs to really be to the manufacturer spec. It's not, you're in uncharted territory if you start rewiring and changing the length and using different materials and stuff like, and if you use wire nuts, I'm going to disown you. We don't do that on cars. We do that in the houses. That's okay in houses, but it needs to be in a box. All right, or the diameter. Smaller diameter, more resistance. Larger diameter, less resistance. All right, so wouldn't it be better if we used a bunch of big old fat wires? It would actually be less resistance, but you know the main problem? It could have the potential to flow more amps, less resistance, that's all good. But the problem is we don't have room for that. We got like 4 miles of wire inside that car. And if you use big wire, 4 miles of big wire is going to weigh more than the car. They're only going to use wire as large as it needs to be. But if you do a repair, you can't undersize the wire. You can oversize the wire, but it's kind of like, you know, it's not, ideally you want to use the same size if you do a repair. So when we look at this, these computerized circuits are going to be very minimal in size because they're not designed to carry a lot of current. So they're going to be very small, which means they're even more like exposed to corrosion causing resistance issues and voltage drops. And then with temperature, just so you know, when you heat up a wire, you change its resistance. You increase the resistance a lot. So let's say that you got a car that's, you know, you want to modify it and you put headers and all this type of stuff. Well, if your wires are kind of close to your headers, you just increase the temperature of those conductors, those wires. You just added resistance. It can cause some things. They can also catch them on fire, melt them, harden. They could do all sorts of issues. Don't ask me how I know. I'm just letting you know. All right. So applying electrical to this. Then if you look, this wire has been maybe this one was damaged by a varmint. They chew. And they didn't maybe totally make an open, right? If they chew through it, it's an open. That would be like no voltage at the sensor. But if they chew it almost all the way through and there's just a few strands, that would be, like a big drop. Like if you had 12 volts going through here, you might only get 1 volt over here at the sensor. Or if it was just slightly nicked, you might get 11 volts rather than 12, right? But either way, that's still going to throw the sensor off or make the ECU not power up. So that's application. Or if we have like a ground with corrosion that's very rusty, that's going to increase the resistance. That's going to cause a voltage drop there. Now, rather than your ECU getting to drop 12.6 volts, and instead it only gets to consume 11.6 volts, that's going to cause some problems. That's a 1 volt drop. That's too much, remember? 0.2 would be the max. Cool. So you might literally have an electrical problem with the ECU that could just be this corroded ground. There's TSBs for corroded grounds causing all sorts of issues, codes and symptoms and issues, okay? All right, pretty fun. And then if you look at, just simply electrical application, we could do the math on this, but if you've got, 12.6 volts and you've got a 10 ohm bulb, and then the switch is good, it should have 0.1 ohms or less. That's going to give you a specified amount of current. Does anybody know how we would calculate that? Ohm's law, right? And you could do, okay, E, I, and R. E would be 12.6. I, we don't know. R would be 10 ohms, but with the switch and the wiring, maybe 10.1, right? So you could do the math on how many ohms is going to be, but that's not exactly what I'm trying to do with this one. But just understand this. This is the tattoo. You should have it. If the volts push harder, the amps are going to be more. So if we have higher voltage, it's going to increase the amps, right? And that's not commonly what we do. What we might do, though, like look at this switch. What do you think that switch could, what do you think a failure of that switch could be? That switch has got contactors, right? Like this, contactors. So what if it's corrosion on the contactor? Well, what if it's just a little bit of corrosion? It should be 0.1 ohms or maybe even potentially like 0.2 or less or so. We would be dropping voltage, should be dim, exactly. So if we increase the resistance by accident, it's going to decrease the amps. Look at this. If we increase the ohms resistance, that means, Mason, can this be you? Yeah. Mason pulls up harder. Mason is the ohm guy. He pulls up really hard. That's going to reduce the amps, right? That's what's going to happen. That's Ohm's law. So if you look at this, if we increase the resistance right here, that's going to lower the amps in the system, and then you're going to get a dim bulb. Except in engine performance, we're probably not dealing with a ton of bulbs. It could be bulbs, but we're dealing with other things. We're dealing with motors. We're dealing with sensors. We're dealing with solenoids. We're dealing with relays, actuators, right? So if we have unwanted resistance, that's going to make, for example, the bulb dimmer. What if this was a motor, though? The motor doesn't glow. What's the motor do? Yeah, or like turns, like it turns, exactly. So if resistance makes a bulb dim, what would it do to a motor? Weak or slow, exactly. Boom. So that's how you can apply that to, a motor. It's the same type of issue. If we have a lot of corrosion on the switch, dim bulb, slow motor, etc. All right, so this was going to be electrical circuit. So this is the same thing. You notice that? Right, it goes through the fuse, through the switch. If we have corrosion right here, this bulb is going to be dim. But you'll notice that's not exactly a bulb. But if it was a bulb, it'd be a dim bulb. But what if it was a motor? Same thing. if you have corrosion on this switch, or you have corrosion on the ground, or you have unwanted resistance right here because of a two-legged varmint. Wait a minute, a varmint chewed the wire. What'd the two-legged varmint do? Who's the two-legged varmint? Yeah, that's right. That's us. So you got the mechanic in there, and the mechanic's like, those that have power, and starts poking and stabbing and prodding and cuts the wire to get a test point, stabs the wire to get a test point. And then a year later, in the corrosion and the weather and whatever, now you got a bunch of resistance in this wire. That's going to make this motor turn slower, right? Makes sense? So it's very important when we do these testing that we do back probing. That's not going to like damage the integrity, reduce the integrity of the circuit, so that wire's enclosed in like a nice insulation. You can't be stabbing that and cutting that and poking at it unless you want to give somebody a bunch of problems later, right? So two-legged varmints are known to pierce the insulation when testing. Two-legged varmints are known to maybe they go to back probe right here, and they front probe with their terminal, with their fluke meter lead that's too big, and you had like a nice connection for the male and female terminals, and instead you get a and now there's not really a good connection, right? So two-legged varmints can be the cause of a lot of electrical faults in engine performance. Cool. So you guys can understand the motor. The motor is basically the same as a bulb, except it doesn't glow, it turns. And we could make that anything. So remember, in electrical, there's a load in the circuit, right? This load could be, I don't know, maybe it's the coil for that relay. Maybe it's an injector. Maybe it's the oxygen sensor heater circuit. Like whatever it is. Remember how we did inputs and stuff? We did inputs, the oxygen sensor is an input, but the oxygen sensor, when it's a heated oxygen sensor, can also be an output. The ECM will send voltage, and that voltage will go through that heater as a resistor, which will make heat, which will heat up the oxygen sensor itself, so that we can start reading it at 600 degrees sooner, right? So if we have the load right here, the load is the sensor for the heated O2 sensor. We troubleshoot it, well, just like back here, if it's a bulb or a motor, right? We're going to troubleshoot it the same as A6. So let's say you're wanting to test this sensor heater because you have a bank 1, sensor 1, oxygen sensor heater circuit open, and you're like, oh, sensor circuit, oh no, heater circuit open. You're worried about the heater grid. You'd go in and be like, okay, 12 volts comes from the battery, it goes through a fuse, it goes through a switch, except if it was a heated O2 sensor, the switching would actually be done in the ECU, right? The ECU essentially is the switch for that. The ECU gets the 12 volts after the fuse. Remember how we had the, I forgot what the fuse was, ECU-B or something? Let's take a quick look. EFI fuse in this case, right? And that could vary on every model, but if you look at this switch, this is the EFI fuse. This switch literally is inside the ECM. So when the ECM wants to give voltage to the sensor heater, the ECM will close the switch inside. Do you think there's any possibility that that switch inside the ECU could potentially maybe fail, like with corrosion or something? It can, but we got to be able to test it. You can't be like, oh, I got a sensor code, let's just jam a sensor on there. Makes sense? Like, you got to test it. So if you're expecting 12.6 volts coming out of the ECU, you know what you could do? Measure it, fool. You got to measure it. Then you know if it's actually like what it's supposed to be. Makes sense? If you measure it and you're only getting 8 volts out of there, you're like, whoa, wait a minute. What's up with the switch inside the ECU? Now you're actually pinpointing, I think the switch in the ECU is defective. Then you could go even further and you could say, like, what's the voltage going into the sensor? What's the voltage coming out of the sensor? So here's one that will blow your mind. What if I showed 12.6 right here and 12.6 right here? How could there be 12.6 on the ground side of the heater? True, it doesn't work, but there's no, because the ground would be gone. If you lost your ground, the voltage would go through the load and the voltage would end up where the ground normally is because you have an open ground down here. So like literally you could think it's an ECU or the sensor, or remember how it could be the harness. Maybe you have a ground wire that's cut, chewed, damaged, high resistance, you know, et cetera, right? So just bringing it back to here's how we would diagnose a basic electrical circuit, and then applying those same concepts to, say, a motor or any sort of electrical load. It's going to be the same. It's just going to look different, and it's going to give you a different symptom. So if you had the bulb, you'd be like, oh yeah, the bulb is dim. Let me see if there's corrosion on the ground or corrosion in the switch or excessive resistance somewhere in the circuit. And I think you could probably understand that with the motor, right? If the motor is turning slow, you're like, yeah, this motor seems like it might not be getting the full 12.6 volts and a good ground. But that's the same for any load. So if your O2 sensor heater circuit was not heating up the sensor, yeah, the open could be in the heater grid itself, but it could also be on the ground, and it can also be in the positive, and it can also be in the ECU, right? So remember what I said earlier. You got a problem. It could be the part that's mentioned in the code. It could be the wiring, or it could be the ECU. This is the same. It could be the part right here. It could be the wiring here, or it could be the ECU, which contains the switch. Okay, like again, it's going to be very similar. What else could it be? Well, maybe it's a resistor, a variable resistor, a potentiometer, a light dependent resistor, a switch, a transistor. And a transistor, that's something that I cover a little in A6. But the thing is, to be honest, ECUs don't have typically switches that open and close, because how do you really open and close a switch? It's like it requires movement or magnetization. So what an ECU is really going to use is going to be a transistor. So for your practical understanding, you can just picture a switch in there. You can test it kind of like it's a switch in there. But just so you know, because I don't want to lie to you, it's actually going to be more like a transistor. So if we had voltage coming into this transistor and we wanted to send that voltage to the heater, it's too hard for an ECM to open and close a switch. So it uses a transistor. We actually control the connection of the in and the out using the base right here. Okay, so test it like it's a switch. Technically, it's a transistor. So if you diagnose that the ECU has a bad switch, it's probably more like it has a bad transistor, which sometimes we'll call a driver. Right? If you hear the term, oh, the ECU's got a bad driver. To control an injector, the ECU is going to be pulsing a transistor, and that's going to give the injector 12 volts, 12 volts, 12 volts, 12 volts, 12 volts. Right? But if the switch, really the transistor, fails, it's not going to get any 12 volts ever. And you'd be like, oh, it's a bad switch in the ECU, but technically it's really a transistor. But a lot of manufacturers will call it a driver. It's an injector driver. This dedicated transistor pulses those injectors. Now, what totally tripped me out was, I learned about it in school somewhat. I was kind of paying attention. I was paying as much attention as I could. And then when I got on the job and I look at the diagrams, the ECU is just this blank box. It doesn't show that the transistor's in there. So part of the reason I like to spend a little time on this is like, you're going to look at the ECU and it's just going to have a wire coming out of a blank box. It doesn't show you what's actually in there. And so, having moved up and got to the point where I can speak occasionally with some engineers and stuff, I asked about as high up as I can go, a Toyota service training specialist who has to go to Japan periodically and is teaching material directly from the engineers. I said, like, what's up with that? Is there beef or what? Because like, don't you think it would help me diagnose if I knew what the heck was in that ECU? Like, I'm kind of guessing sometimes because it's not on the diagram. And he said, oh, yeah. You're right where I was at. I asked the same question. I went to the Japanese engineer and I said, hey, how come you have all this blacked out? Like, it's just blank. We need to know what's in there. And they said, like Daniel-san, too many questions. Too many questions. You don't need to know. Sort of like, what you mean I don't need to know? All right, so I understood a little bit more. The electrical engineers build all the complex integrated circuitry and they put that all in there. They're not going to give you a diagram of it so that you can print it off at your job and then go over to Honda and or Mitsubishi and be like, hey, look at this. Why hire an engineer to custom design this? I'll just give you the whole diagram and you can just replicate it, right? Like that's kind of what China does. You know, they take our designs and they copy them cheap and they sell it cheaper. That's what they do. You got to be honest, right? So they're not going to tell you what's in that ECU because they spent hundreds, if not thousands of hours developing and researching. And so sometimes what we do is a little bit of a mystery because they don't show you everything that's going to be in there. Okay. Sadly. But the good news is, and I'll jump on service information. I'll show you some things that I've learned. If you can get access to all the information that they do put out, you can pretty much figure it out. You might not know exactly how or why or what type of transistor it is or whatever, but in your mind, it's okay if you're diagnosing a switch because you're going to test it kind of the same anyway. We have no ability to access the base. We have an ability to access the output of the transistor. So if it's a switch or transistor, who the heck cares? And by the way, another load could be this coil side of the relay. Remember that? We were kind of talking about that. The coil side of the relay, if it gets 12 volts and ground, is going to actually magnetize and pull the switch contacts over on the relay. So if you see that, know that's the load. It's going to be very important for you to identify in a wiring diagram what the load is so you can predict what the voltage should be. Okay, that's all over the place. And another really cool one is a light emitting diode. LEDs themselves aren't actually a load, but when you have an LED, they're also going to have resistors with this LED. So it kind of becomes a load because it has resistors, although they may not show them. To make an LED work, they need to drop the voltage way down. Cool. So that would be an output. That would be a load. That would be a load. Half of it would be a load, actually. The left half, the right side would be a control device, which is like a switch. The transistor is more of a control device, although technically this side is a load. That's all inside the ECU. We can't test that. You can't test the actual circuitry inside the ECU. Circuitry inside the ECU is like a printed circuit on that green board, like semiconductor material, and it's the whole, that's a different thing. That's not really what technicians do. Now, there may be someone who does ECU rebuilds and overhauls and ECU advanced testing and repairs, but they just do ECU stuff. Technicians, we don't really go that far. Like, if you want to know how far we go, I'll back up and I'll show you. All right? And don't worry, you guys have access to this. So if we're to back way up to this diagram, we can test right there. We can't test right here. We can't test right there. We can test right there, right where the circuit comes out of the ECU or goes into the ECU. We can test that far. That's it. We don't get to test inside. So as long as you can identify that the problem is inside the ECM, we're done. We don't need to go any further. We don't need to do any more, right? So enjoy those diagrams. Now, when we start to do these tests, what do you think the main workhorse tool is going to be? Yeah. DMM, DVOM, it kind of depends on who words it, but DMM has become a little more popular. So you got a fluke, it's going to show your voltage. You can select different ranges. I would say probably leave it on auto. You could select the modes. So you could do volts, ohms, AC and DC volts, ohms, amps, AC and DC amps. And a lot of times it'll even give you different scales. Input jacks. So like basically we're going to do, the red lead is going to be on volts, ohms all the time, and the black lead will be on common. Rarely, if we have to test amperage, which is not very common, we might have to move the red lead over to A and make sure that you put it on amps because that's the 10 amp fused port, right? So if you can see here, you can get an idea. This is a pretty nice meter. This meter can do pretty much everything you need. All right, so if you took electrical, this should be review. If you didn't, pay attention. Okay. Let's say that we want to do some checks. Let's say right here, we're going to check for voltage, right? We would assume this is going to be 0 volts ground, 12 volts here. 12 volts should go through the switch. If the switch is closed, 12 volts to the load should consume all the voltage. which means coming out of the load, we should have just about 0. So if, the way this is set up, we're going to set up a few different ways. We just checked available voltage. We stabbed the black lead on the ground. It's just hanging there on the negative terminal of the battery with an alligator clip or whatever. And then if we're taking this red lead, we should have 0 volts after the bulb, right? Because the bulb is the what in the system. Think of back here. Exactly. If the bulb is the load, we want the bulb to consume pretty much all the voltage. So we should have 0 left over. Do we have 0? Technically, no. We have $0 and a half of 1 penny. So that's pretty much, you're broke, fool. If you have a half of a penny, that's not even enough. That doesn't even register. That was, oh, I can. I absolutely can, because I've been there. I'm allowed to. And I can tell you stories, but I'll hold them for right now. Which is part of the reason I wasn't able to pay all the attention I could in school, because I was not really getting enough sleep, but I was just barely scraping by. So if you look at this, that's pretty much 0. You've got not a tenth, you've got a half of a nothing there, right? That wouldn't even show up typically on the meter. So you're good. That has 0 volts after. Coming into it, you should have source voltage of 12.6, right? And we'll show that, but this would be using the meter to check available voltage. And you could pretty much diagnose any circuit you need with just available voltage. So we'll focus mainly on that. We will flip it to some voltage drops because, you know, that's another way to do some good diagnosis. But for this one, this will be the main way we do this. And so if we were to look at this, and let's say that we wanted to measure resistance, we would actually disconnect the circuit and we could put the 2 leads wherever we want and switch it to ohms. And that will tell you what the resistance is between the 2 leads. Typically, we want the red on the more positive and the black on the more negative. But in reality, you could actually switch it the other way. It's not a really big deal. This is just telling you what the resistance is. On this picture right here, what are we measuring? We're measuring resistance of what? It's resistance of a component. What is between the red and black lead? The ground wire, exactly. So if you thought that the ground wire was no good, you could usually test it with voltage, available voltage, voltage drop. But like, just so you know, if you want to measure resistance, you just put whatever it is that you want to measure between the red and the black lead, you put on ohms, it'll give you a number. The resistance of a wire should be pretty much 0. Maybe 0.2 is what the meter would read, but pretty much 0. Okay. So you could do available voltage, you could do resistance. Some people may call this continuity. Like if you have good continuity in that wire, it would say like 0.0 or 0.2. You could even push a little button on the meter, like on this back page right here. You see this thing? Doesn't that look like sound? You can put it on that setting and press the select button, and it'll make it so if you have good continuity, it'll go beep, right? So sometimes I'll do that, and I'll be like, is the wire good? Beep, yes. Is this wire good? And I'll put the positive here, and I'll put the negative here. And if it's got good continuity, you know what it'll do? Beep, right? So just remember this. If you diagnose it as an open wire, sometimes it gets confusing, and sometimes you're like, your brain's a little overwhelmed, and it's like, this is a mess. You can always take a step back and just put on the continuity test and make it beep. And if you hook up to one end of the wire and the other end of the wire and it doesn't beep, that's definitely an open. Makes sense? So like sometimes it's about being able to test for a failure in 2 or 3 different ways just to be sure that it's correct. Okay. All right. So let's say that we're going to do some voltage dropping. In fact, I think I'm going to switch the order. I thought about it. I'd like to switch them. If you look at this, we're going to do available voltage. I'm going to go ahead and I'm going to put the black lead on the ground. And then let's just say I put the red lead up here. I've got 12 volts coming out of the battery, 12.0. So first off, that battery is not fully charged, but it makes easier math when it's 12.0. Right. After the fuse, I have 11.9. Is that good? That's still pretty good, right? You paid 1 penny, actually technically 10 cents to go through the fuse. It goes through the switch. It has 11.8. Is that switch good? Yeah, I mean, you're only dropping 0.1 volts. That's pretty good. That's 10 cents. I'm happy to pay 10 cents to use the road. You start charging me $1, I'm mad. $24 westbound on the 91 freeway using the express lanes in rush hour. 24 bucks. Scams. All right, but we're only starting with 12, so you can't charge me 24 if there's only 12 available. Okay, so we went 11.9, 11.8. Sounds like that's pretty good for a switch. Then we went through the dimmer, and see, we're going to slightly change this. Let's not make this a dimmer. Let's just say this was damage caused by the two-legged varmint. If we're testing a wire and we have 11.8 going in and 7.1 coming out of the wire, why is that dropping so much? Yeah, it's got like, if it was open, it would drop to 0. So if it dropped from 11.8 to 7.1, that's high resistance. Why is it high resistance? Maybe corrosion, maybe it was chewed, maybe there's a connector right here and the connector's loose or something, right? But boom, you just found a problem in the circuit. You know that wire shouldn't drop 11.8 to 7.1. If you look at the drop, it just dropped 4.7 volts. That's way too much. We should never be dropping 4.7 on a wire. That's bonkers. All right. And then by the time we get down to the lamp, we got 7.1 coming in, and then we've got 0.1 coming out. So we were at 7.1, they were at 0.1. That lamp dropped 7 volts. You see, that's okay. But in this circuit, this is the load. What should the load have dropped? Yeah, like pretty much all of it. Yeah, about like 11.8. If we were to have 11.8 right here and it were to have made it down to here, it would go from 11.8 to 0 or 0.1. That bulb would be nice and bright. Why is this bulb dim? It's only dropping 7 volts. Why is it only dropping 7 volts? Because it's sharing voltage with this damage from the two-legged varmint. Make sense? You can. Yeah, you can. And so when you're diagnosing, let's say that this bulb was actually, how about that oxygen sensor heater? And your O2 sensor heater wasn't really getting hot enough, and it it had a code set. You could actually just go ahead and check 11.8, 11.8, 7.1. Wait a minute. That oxygen sensor heater is only going to drop 7 volts. It's not going to get hot enough. So yeah, you could back up and verify that you have 11.8, come down and verify you only have 7.1. Why is it dropping so much? If you really wanted, you could actually temporarily splice in a wire to make sure it gets the correct amount of voltage down there. It's just you want to track this down and actually repair this really nice. That's pretty much what we do. So your whole check engine light problem, and you thought it was a sensor, turns out to be some damage, some corrosion, some whatever in the wire. Makes sense. It happens all the time. And that's exactly how you could track it down. You need to know what voltage should it have. Check it, check it, check it, check it, check it. Whoa, wait a minute. That's not what I predicted. I predicted we'd have 11.8 right there. Why did I lose that much? Someone's robbing me. Kind of makes sense. So I want you to just take a quick look at these. We dropped 0.1 volts, 0.1 volts, unintentionally 4.7. We dropped 7, then we dropped 0.1. Well, what if we were to go to a voltage drop? Available voltage is great. The difference between these two is this one, your black lead stays on the known good ground, preferably the battery terminal, and you're moving your red all throughout the circuit, right? Poke like this, like poke, 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 right? When you voltage drop it, it's a similar test. It's just a little different style. You're not leaving the ground down here and poking. You're moving both of them. When you're voltage dropping, you're measuring the voltage drop between the red and the black. Okay, between the red and the black is what we're doing. If you're measuring between the red and the black, you have to know what the expectation is. So if I'm measuring voltage drop of a fuse, I'm expecting 0.1 or maybe less. 0.1 or less would be pretty good. So if you look at that right there, 0.1, and the switch, 0.1. Those are both good, right? But I'd move the leads together. 0.1 on the fuse, 0.1 on the switch. Then I go to measure this wire, and that wire drops 4.7. How the heck is that wire dropping 4.7? I would already know the wire has excessive voltage drop, right? Different ways to do it. You do it this way, you do it this way. You know why I'm showing you both right now? ASE will ask you both ways. ASE will have a diagram like a this. ASE will have a diagram like a this. And so you got to be able to know, you got to be able to do it both ways. Okay, cool. So far makes sense, kind of? All right. Another way you could test that. Let's just say, remember that dimmer was damaged by the two-legged varmint. You could measure the resistance of that wire. The resistance of that wire should be about 0 ohms. If you measure resistance of a wire and you get 16 ohms, no wire should have 16 ohms. That's a fail, right? So sometimes just to like really be sure that I'm not tripping, I'll measure available voltage. I'll be like, that's wrong. I'll voltage drop it. That's wrong. I'll measure resistance. That's wrong. Like I know it's wrong. I can prove it's wrong in 3 different ways, you know. And sometimes I don't do that because that's kind of redundant. And if you're confident, you know it. Like you tested it, it failed, you're moving on. But once in a while, if it's something that's expensive and something that I'm sketched out about and something I think that might go sideways, I might employ several different tests to confirm my diagnosis. Kind of make sense? All right, good. You can do this. All right, here's a sample A8 question. I'll read it to you. I'll talk you through it. A vehicle is being diagnosed for a cylinder number 4 misfire detected. The DTC is stored. During diagnosis, the technician observes no spark at cylinder number 4 ignition coil. Using the schematic shown and open at which of these could be the cause. So if you look at this, let's talk through. You see Y? What is Y pointing to? What's that part? A fuse. And that fuse goes, look at this, that fuse goes to the ignition relay. And if the ignition relay is powered up, it'll actually go ahead and it'll power all these coils. If that fuse was blown, what do you think the symptom would be?
All of them.
Exactly. No coils would work. It would be all of them. The car wouldn't start. The car would no. What is this car in for? Remind me. Okay, so if it's a cylinder 4 misfire, we could probably say that it's probably 1 coil not working, right? If it's 6 coils not working on a 6-cylinder, that car doesn't start. It wouldn't have driven in with this code. It would have got towed in as a no start. Make sense? So do you think the problem's with W? No, cross it off. And yes, I left the answer selected, so that's okay. What do you think about Y? What does, let's find, oh, I already picked Y. I'm sorry, it wasn't W. I was pointing Y. Let's look at W. What does W do? That's a ground, but for what? Remember what that does? Remember the biology instructor who calls IT for the computer that doesn't work and comes to find out it's not plugged in? If that ground's not connected, what's that gonna cause? The whole PCM isn't gonna function. You think it came in for a misfire? I don't think so. That one also came in for a crank no start. No. Right? So again, now we're putting to test, you understand what we were talking about. So if it's like that, don't you think we could safely say it's not W? Yeah, so it's not W, it's not Y. I had those out of order. That was my B. Let's take a look at Z. What's it look like Z is doing? 12 volts goes to the coil. When we go to power up the CCM, we're probably going to want to like energize that coil, close this, and give power to the coils, right? So if this is the load in the circuit, right? That's the load. Matter of fact, we can even trace this. I can do that. It makes it a little bit tough. Let me see if I can pull this over right here. All right, so this should be red, right? In this case, orange. Boom. Now that's the load. So to make that load active, what would we need to do? True, we need to give it a ground. Okay, so the PCM will apply a ground like this, right? If it closes this switch, click, boom, now it has ground. This gets magnetized. What happens? It pulls this down. And then as a result, what happens is voltage will go through, power the coil. Okay, makes sense, comes around, power the coil, power the coil, power the coil. So what is the ECM providing at point Z? It should, yeah, exactly. Do you think the problem is at point Z? If the problem was at point Z, what would it cause? Once again, no coils would work because no coils would have the voltage to work, right? So honestly, this is kind of an engine performance question, but to me, it's really more of a, it's really like more of an electrical question, I would say. I need to remember how to trash those, all of them. There we go. Okay, good. All right, that one makes sense to you guys? Now look at X. X is a connection where this coil is getting its signal. So right here, you notice this has a little transistor. So this PCM, see, this box is blank. And I'm like, hey, why can't we see that? And they say, you don't need to know. You don't need to know. But we kind of do. But this is what I could tell you. It's part of my job. If this coil is getting, see, this is getting voltage from here. It's getting ground from here. This is the actual spark plug. You know what I know is happening on this wire right here? The PCM is giving it some sort of signal. It may be pulsing 12 volts. It may be pulsing ground. I don't exactly know. So, you know, for me to know, I'd have to go in the service manual and I'd go to like terminals of the ECU and I'd say, hey, what's the expected voltage at point X? And I could look that up and I'll show you how. It's a pain in the butt. But I know that what it should be doing is sending some sort of signal because the PCM sends a signal to fire the coil, right? If I had to open at X, which coil would it affect? That's it. Just that one. Number 4 right there, cylinder number 4. So if cylinder number 4 coil is not working, what's the car come in for? Misfire. And it may literally be because there's a bad connection at the coil trigger wire at the ECM. So X is the one that makes sense, right? It's just a straight up electrical question. Now we're going to cover ignition systems in detail, but we're just trying to apply electrical. I'm also trying to sell you on, hey, the electrical stuff is very electrical on engine performance. All right, how about this next one? Don't you make fun of my drawing. Okay, this was like a repurposed drawing, and then I accidentally cut the end of it off, so I redid it. All right, I'm going to read it to you because I like to do that. Based on the chart, the code chart provided, which these diagnostic trouble codes would most likely result from an open circuit at G300? Okay, we'll do an overview. The DLC, do you know what that is? It's where you plug in the scan tool. So we'll do networking more in detail, but if you understand, when you plug in the scan tool, this ring right here, this little circuit is how you connect with all the other computers, right? So there's the high, it's going to go to the PCM. And then there's the low, which is going to go to the PCM. And the high is going to go to the TCM. And the low is going to go to the TCM. And the high is going to go to the ABM. And the low is going to go to ABM, right? And then at the very end, and this is where it got cut off on accident, my apologies, SCCM, all right? The SCCM. Now, if you notice, this is the PCM, remember? So let's just say that we had no communication with the PCM. The PCM needs the battery voltage, it needs the ignition voltage, it needs the ground. We all agreed on that, remember? That's just the same as why we call IT when we teach biology, to change the screen settings. And then if it's got 12 volts here and it's got 12 volts here and it's got ground here, is it possible that we could plug into the network and still not communicate with it? I mean, it's possible. What if we had like an open here, an open there? Or what if we had the PCM didn't, what if the PCM was no good itself? It would cause it to not communicate, right? So the checks that we're going to do are check this voltage, check this voltage, check this ground. If there's any problems with those voltages or grounds, find out why, because that'll make it not communicate. Cool. But if those are good, we need to check to make sure it's getting can high right here and can low right here. And if it's not, then we need to figure out what's wrong with the network circuit. Okay. But if it's getting battery, ignition, ground, can high and can low, that sucker better work. And if it doesn't, It's kind of like a bad employee. If you give a bad employee everything they need to do the job and they still don't do it, what do you need to do? That's right. Let's make it less personal. What if it's a professional athlete? If that athlete is getting enough, it's a wide receiver. They're getting the ball thrown to them. Their training camp. They have the personal trainers. They have the people to give the massages. They have the water. They're getting paid enough money. They got everything they need to be successful. If they're not successful, like, I'm sorry, it's time to trade them. You know what I'm saying? Time to get a new one. Same with this PCM. But if that professional athlete is not getting the nutrition or not getting, I hate to make it about pay, but really, if the athlete's not being paid that well, sometimes they get a bad attitude, right? You could fix those external things. Make sure they've got battery voltage, ignition voltage, good ground, connection to the can high, connection to the can low. If you got a problem with that, you got to fix those first. Then you'll know if you got a good module or good wide receiver or not, right? In this case, though, here's what we've got. If we had an open on G300, what do you think that would affect? This is G100, G100, G105, G300. What do you think it would affect? What do you think it would cause? What would it do? All right, let's look at this. What is a U0100 DTC? U0100 lost communication with the PCM. Do you think that G300 being open is going to affect the PCM? The PCM uses G100. We don't care about G300 for the PCM, so I'd say no. How about 101? 101 is transmission control module. Transmission control module uses G100, and it has its own ignition. So I don't think it needs G300. It doesn't need that. That's not important. What about lost communication with anti-lock? That's got its own ignition, battery, and it's got its own ground, which is separate from G300. I don't think so. However, lost communication with steering column control module. Oh, steering control module, that uses G300. If G300 is no good, steering column control module will not power up, in which case you'll have no communication. Does that make sense? What if we had a problem with G100? What do you think it would have? And, all right, so if we had a PCM U100 and a TCM U101, I would be all over G100. Why? Because G100 is used for both. Exactly. So you just took a complex networking problem, boiled it down to just simply being an electrical problem. That's it. You're going to do this over and over and over. If you understand it pretty well, it's not that hard. All right. Now, let's look at what the ECM is doing as well. So here we've got the ECM has a bunch of inputs. You guys remember inputs, right? Those are like sensors. They measure, they observe, they tell things. For example, a switch. You guys know what a switch does? On and off, and that's it. So that switch could be maybe like, for example, a park neutral switch. Okay. If you're in park or neutral, that switch will be closed. What if you're in drive? That'll be open. All right. So here's how that kind of looks. If you look at this switch right here, I'm gonna also I'm gonna draw this because this one I specifically used. Whoops, I specifically used ECM with the diagram that's inside of it printed. But just know when you look on the real wire diagram, it's not gonna be there. Okay, they're not gonna give that to you. All right, and then I think I'm gonna drop one light because I think you'll be able to see a little bit better. All right, right here, we've got 12 volts, right? Or we've got some amount of voltage. Cool. Now, what is that thing? That's the load in the circuit. So what should we have after the load? It should be ground, but it depends on the status of the switch. Cool. Where's the switch right now? Open. So guess what happens? Voltage will go through the load and go all the way to right here where the switch is open. You get me? So this sensor right here, this circuit in the ECU is is monitoring voltage. So see how it says a V, that's a voltmeter. So right there, what is the voltage that this is monitoring now? Give me the number. Exactly. So if this ECU is showing 12 volts, what's that tell me about that switch? It's open, that's what I'm saying. All right, now let's just say the switch gets closed. We close the switch because now we put it in Parker neutral. Now what do you think is going to happen? Ground is here, right? Ground is going to walk back to here. But now that the switch is closed, guess what? This is all going to be ground. So what's this voltmeter inside the ECU going to read? 0, exactly. That's exactly what happens inside the ECM. The ECM is just going to monitor voltage, and sometimes we'll call this thing right here like the sense circuit. If it's monitoring on the sense circuit and it sees 0 volts, the switch is closed if it's a ground side switch. And if it sees 12 volts, that means the switch is open. Okay, that's how the ECM functions electrically. Cool, you like it? All right. The rest of these could be a bit complicated, but I'll consider covering them. I may cover them a little bit. I'll probably need to cover them twice, to be honest with you. All right, so if I look at this, if I go with this, 12 volts is going to go to this resistor. But then what? Because this is kind of confusing, don't you think? Isn't that a little bit confusing? Like that's a resistor and that's a resistor. All right, how about this? We're going to make it 5 volts because that's what we would normally use anyway. The ECU, when it does sensors, a lot of times uses 5 volts. And it's 5.0 volts. Remember how I was talking about how the system has a source voltage of 12.6, but it might be 13.9 if it's running? All right, the ECM regulates that to 5.0, clean, accurate, no matter what your engine RPM is, volts, because it needs it as a reference. So when I say a 5-volt reference, it made a voltage that's very stable, so it gets a consistent reading. Then it's going to go through this resistor. And so if you look at this, we got a resistor here. I'll circle. We got a resistor here. We got a resistor here. What type of circuit is that? Remember any of the circuit terms? There's 2 loads in there. That'd be series. In a series circuit, these 2 are going to share the voltage. So let's just say this one is 1K ohm. And let's just say this one is 1K ohm. Aren't those the same size resistors? So if we were to bring this back to how I taught electrical, it's like the parents have an allowance that they gave out of $5. Don't spend it all in one place, kids. But you've got 2 kids and they're the same, equal size and strength, but they have to share the $5. How much are they going to get a piece? All right, so this is going to drop 2.5, which means we have 2.5 right here. Then this is going to drop 2.5, which means you have 0 here. You get me so far? Kind of, or no? Because there's 2 resistors. This one is a fixed 1000 ohm. See how this one has a line in it? This is a variable resistor. That resistance will change. For example, if it's coolant temperature or air temperature, right? So the resistance of this sensor is going to change. If they both happen to be 1000 or sometimes 10,000 ohms, you're going to get how much on the sense circuit right here? 2.5. So if you've got a 2.5 volts right there, you're like, oh, okay. I know. That's how the ECM can verify what the actual resistance of the sensor is. Kind of copying so far? When I went to school, my instructor kind of fibbed to me. He was like, oh yeah, the ECM measures the resistance of the sensor. But then I was looking at the sensor and I was like, I don't think it's measuring the resistance. How does it know? Well, I just described to you, it's checking the voltage drop in between. It's the available voltage in between. This is called a voltage divider. So if you have a fixed resistor and a variable resistor, depending on how much the fixed resistor consumes, we can tap a sense circuit after it. And depending on what that voltage is, we can calculate mathematically what this resistance is. Okay, that's how it actually works. Okay, kind of crazy, huh? Remember, you don't know what's inside here. You don't need to know. You don't need to know.
I'm just going to try to red pill you as much as I can. Get you out of that matrix. You need to know everything you can know. All right, then in addition, we've got sensors that are going to work on frequencies. So like, for example, we might have a AC sensor that measures AC waveform, knock sensors, maybe a cam position sensor, or we could have a DC sensor. That's going to be a square waveform. So this can tell us on or off. This can tell us a number of different variable things. This can tell us AC speed, and this can tell us DC speed. There's times to use AC, and there's time to use DC. DC's on the rise. DC can tend to be a little more accurate, but it's a little more expensive. So if we just need basic speed, we'd use AC to save money. All right, and then if we have a variable voltage sensor, for example, an O2 sensor, the O2 sensor itself is going to generate a voltage based on the oxygen content. So if it's lean, it'll be closer to 0 volts. And if it's rich, it'll be closer to 1 volt. And the ECM will literally measure the voltage right there and be like, oh, look at that. We're at 0.45 volts. That's perfectly stoichiometric. Makes sense? So electrically, that's how these sensors are working. And we will go in a little bit more detail on those, like especially with a 3-wire position sensor, but we're going to cover every sensor at a later time, just so you know. And by then you'll be pretty familiar with how they work electrically, so it'll be good timing. All right, now if we look at this, we've got a couple different types of switches here. So if you look at this, if I were to draw this, look at this one. See that symbol? You know what that symbol is, right? All right, so if we were to trace this, I would have to go ground like this. But then guess what? The ground kind of stops right there, because what's that thing? All right, interesting. So what really happens? Well, let's trace the positive. What do we know? B plus is positive. What's the status of the switch? Right now it's open. So do you know what happens? The ground will actually go all the way to here, which will mean it's getting 0 volts. So that switch is open. That would mean that we're actually sending 12 volts to the switch, but see, the 12 volts dies right there. It's gone. So what if we close the switch? Then 12 volts will go through the closed switch to right here. And it'll stop right there because that's the load. So this load will consume the voltage, right? In fact, I didn't even mean to do that. Which means, how much does this have now? 12, yeah, or source or whatever. Exactly. So that would be a power side switch. But it's also very common to do a ground side switch. So let's start with supply voltage goes down to here. Oh, okay. What's the status of the switch? All right, so it goes through, goes all the way to here. So what's this?
Or no, it should be
12 or whatever, source, supply, whatever it is. Cool. But what if we close it? Then what'll happen? Close that. Then this ground will come all the way back to the load, right? So if the switch is closed, you'll always have voltage on the positive side and ground on the negative side of the load. The load is really where I start. The load is going to tell me what's going to be what. Now, if we have the load like that, I would like to think it's like this, but then you realize the switch is open, in which case you realize it's actually more like this, right? But the load is going to show me where the positive ends and where the negative starts, assuming that there's not this. Do you know why it works different with this? This switch, how many ohms do you think this switch has? Like a gazillion, bajillion. Like if you put your meter on there, it's going to read OL. Do you know what OL means? Yeah, it means it's out of the limits of the meter, and the meter can read millions of ohms. So it's more than millions. That means that thing's got lots of ohms. Now, if we were to look at this and we were to call that a 1 kilo ohm, 1 kilo ohm is a big resistor, right? But compared to millions and millions and trillions and billions of ohms, this thing is nothing. So ultimately, this kind of becomes like the greater load, which is why this is going to drop all the voltage. So you would actually get 12 volts, and it might drop slightly. Maybe it was 12, and maybe now it's 11.999, because maybe, you know, with this being 1,000 ohms and this being millions ohms, maybe this consumed a little bit, but you know why it's saving the big voltage? Because this thing, it's not like having equal size and strength siblings. This thing is a beast monster with millions of ohms, and this thing's got like a measly 1,000 ohms. Make sense? This is going to consume the vast majority of the voltage because it's so massive. That's why 12 volts will go to here, and then this side would be ground. Okay, that's just electrically really why that happens. Okay, kind of makes sense how we do the switches thing. All right, so if you wanted to test, this is how the ECM tests it. What if you wanted to test it? How could you test at the ECM if this switch was open or closed? Let's call that terminal 1 and this terminal 2. What would you check right there? Back probe it, check the voltage. If the switch is open, what's the voltage going to be? Remind me. 0 if it's open. What if it's closed? 12. Exactly. So you can also test it just like how the ECM tests it. If you get a code where you believe that that switch is no good, you need to check it yourself. You can't just throw a switch in there. If it gives you a code for park neutral switch and you just throw the switch in there. Because what if, ready for this? What if we had an open right here? Matter of fact, you know how I can make it open? That would be pretty cool. What if we had that right there? All right, let's think about that. Let's make it so the switch is closed. Cool. What would we have here? It would still be 0, right? Because look, the voltage would go through. Oh, the ground would go through all the way to here, because this has infinite ohms. The positive would go like this. But ultimately, the ECU sees 0. So the ECU seeing 0, what's that mean? That means the switch is open. But look, the switch is closed. Why does it still see 0? Because the wire's open.
So you have to backtrack.
You'd be like, but it's got a code for the park neutral switch. And you're like, yeah. But remember, I told you the limitations of the OBD2 system. It can tell that this voltage is 0, and it might even say like, hey, we think that there's a problem with that switch, but it doesn't know if the open is here, 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 there, here. It doesn't know. It doesn't even really know what if the open was here. It would get 0 all the time, even if this whole circuit was working, right? So I just proved to you. The problem could be the switch, but the problem could also be the wire. Or if it's here, where's this circuit? Could be in the ECM. So it could be any of those things. So you get a code and all you really know is, hey, you know what? Remember I told you like last time, we know what state it's in, we know what city it's in, but we don't really know what the address of the house is. You got to go track that down.
If it was there, that would be the floating though, right?
Well, let's take a look. If it was there, it's not, this part's floating, is it's not attached. Well, if the switch was closed, it wouldn't be though.
I mean, like that break in that ECU.
All right, let's say that this is closed. Oh, if this was open, yeah, but it is kind of floating. But if you have a wire that's floating, let's define floating. That's a good question. If I had a wire, let's say this is my wire right here. How many volts are on this wire? 0, because it's not attached to anything. See what I'm saying? If it's floating in the air, trust me, it doesn't have any voltage on it. So 0 volts can mean a couple different things. 0 volts does not necessarily mean a good ground. 0 volts could mean it's just floating in nothingness. Whereas if you were to, and the ECM is going to measure this as 0 volts, but the ECM doesn't necessarily measure it as like, wait a minute, is it 0 volts with good connection to ground? Or is it like just 0 volts that could be because it's broken internally and floating? It doesn't check that, doesn't know that. Maybe someday, but not right now. kind of understand the difference between floating and grounded? So grounded would be if we were to take this sucker and nail it down to a ground like that, they would both be 0 volts. One is shorted to ground and one is just open and isolated, aka floating, which is a term I don't commonly use. All right, so you feel pretty decent on that. How about a sample question? All right, let's look at this. You like these, huh? Vehicles being diagnosed for a crank no start complaint. You know what that means? It's cranking. It's cranking. But people mess it up all the time. They'll be like, "Oh, my car doesn't turn over," and I'll be like, "Let me hear it." I'm like, "Dude, it's turning over right now. I hear the starter running." They'd be like, "Yeah, but it doesn't turn over." I'm like, "Yeah, it does. That's it turning over. You mean it turns over, but it doesn't start? That's a crank no start." Okay, that's what we got. Okay. The vehicle's being diagnosed for a crank no start. The technician observes RPM signal on the scan tool during cranking, but there's no spark at the ignition coil. Okay. Well, just let's pause right there. Whoops. The technician observes an RPM signal on the scan tool. What exactly does that mean? They got the scan tool, right? How are they observing an RPM? They plugged it in. Exactly. So they plugged it in, and this isn't really even showing the DLC. So that's not on this diagram. So you need to be familiar with this. If you plug the scan tool in, your scan tool is a computer that goes onto the CAN high and low network, and it communicates with this computer. Make sense? So if this computer is telling your computer scan tool that it has RPM, where did the RPMs come from? What's that?
Oh, it goes from the sensor.
The sensor is giving RPM. This is ASE's breakdown, right? Right here, it's showing RPM on the scan tool. They don't really give you pointless information. That means something. What does it mean? I look at the diagram, I'm like, oh, okay, crankshaft position sensor's working. Cool, got it. But remember, there's no spark at the ignition coil. Okay, well, here's the coil. There's no spark at the ignition coil. A DMM at point X reads battery voltage during cranking. Oh, it's another drawing one. All right, if we look at this, let's start with pen and red. And if I'm not real worried about all this stuff, I could trace the whole thing, but when I've got an ASE type question, I really want to focus on what matters. I'm really more concerned about what's over here. It should have this to this to that. Beyond that, that's probably as much as I know. Now, if I change over to ground, do you notice this thing right here? Doesn't that kind of look like the load? That is the load. That's the ignition coil, the primary side of the ignition coil. That's the load. What do you think we should have coming out of the load? Oops, that's the wrong color. I got so excited, I forgot to change. All right, so we should have a ground right there, okay? Which means what should X be doing? What should be happening at X? X should be getting grounded. Now look, remember, you don't need to know. Okay, I'd like to. You go in here, and there's actually going to be a little switch, and that switch is going to go to ground, right? And the ground is actually probably coming from the external ground. Okay, so what the PCM does right here is it gives ground and it takes ground away. It gives it and it takes away. It gives it and takes away. But why is it not on there? Well, this is pretty accurate. If you pull the manufacturer diagram, yeah, the PCM is a big blank box. You don't have a clue what's going in there. So you got to kind of already be familiar with this, all right? So the PCM is going to provide ground and take it away. But what was it saying in the wording here? It reads what? Battery voltage. It reads 12 volts all the time. All right, if it's reading 12, doesn't that kind of tell me that the voltage is making it through all the way down to X? So doesn't that kind of tell me this isn't really like, maybe that switch is not pulsing ground? Tracking with me so far? If that switch is not pulsing ground, do you think it has to do with the open engine fuse?
No.
Meh. Do you think it has to do with an open PCM power relay?
No.
Do you think it has to do with an open ignition coil? Let's look at B and D. An open ignition coil primary. We haven't covered ignition, so you don't know all this yet, but we're trying to tie electrical to it. So look, this is the primary coil. If it was open, if this was open, we would actually have gotten ground after the open. Would you agree? But that's not what we measured at X, right? So what's that tell me? D is full of it. If this was true, we would have had 0 volts at X.
Okay, so we're gonna assume-
Because it would have been dropped right there at the open. Exactly. But instead, we have 12 volts. So if we have 12 volts, I'm going to say this PCM is not grounding. An open PCM coil driver, remember I told you they can call it a driver? In reality, it's not really a switch, right? It's actually going to be a transistor, and that transistor is not providing the ground. Boom. Got it? Go ahead.
Or could we get on the outside, there's no ground.
I like that idea, but think about that. What if it was this ground? What do you think would happen to that ECM? That PCM? PCM wouldn't power up. And remember what we said earlier? If that scan tool was able to pull a crankshaft position sensor reading, that PCM's powered up. But see, there's one ASE question has a ton of information packed into it. And it's not, if you understand it, it's easy. But like, if you don't, you're missing pieces to the puzzle. We must study. We must study. That's another thing the Japanese engineers say. We must study. I go, okay, why don't you just tell me the answer? We must study. Okay. All right, and so remember what I was saying, how we have the ECM, has to provide that really clean, stable voltage because your system voltage is up and down and your battery voltage is one thing and your charging voltage is the other. Well, this was a good diagram showing, Toy likes to call it VC. This is voltage constant. So the ECM is going to regulate it and give us an exact voltage. This whole bus, we could call this a bus right here, could be 5 volts, 5.00. If we had a problem with VC, which sensors would be affected?
All-
1, 2, 3, 4, 5. They would all be affected. So if you've got a problem with sensor 1, I don't really suspect an issue with VC. Make sense? But if you had an open on VC right here, yeah, that would be a sensor 1 problem only. But if you had an open on VC here, that would be 1, 2, 3, 4, and 5. Okay, so when we are checking these sensors and it talks about a reference voltage, it's this reference voltage constant that's generated in the ECM. And it's very, very stable. And it needs to be. And the other thing that totally blew my mind was I came out of school, I passed some ASEs, I had the patch. I got the ASE certified patch. I got the tattoo. I didn't get the tattoo. I could have got the ASE certified tattoo, but I didn't get that. I also didn't get the Ohm's Law one either, but I passed all the tests. I was doing pretty good. And I got a car. I couldn't fix this car. It came back like 3 or 4 times. Like it would come back with a crankshaft position sensor code and a crank no start. And I'd go out and it would start. And then I'd be like, what the heck? The code's set. I'd drive it. It wouldn't happen. Like, I don't really know. Put a crankshaft position sensor in it, ship it. It's good to go. Car comes back a week later. Same concern. Car died again. See, back in those days, people were a little more forgiving. I really don't survive well in this current environment. Back then, this customer knew, like, well, they're trying to fix it. They just don't know what's wrong with it. And it was somewhat incompetence, but like, I was like fairly close to the top of the class, at least if I remember, right? And I was like totally stumped on this car. So I look, sensor, I check the voltage. The voltage is good. I check it again. I check it again. And as we get a little further down, I check it with a picoscope. I check it with all this stuff. Like, it's good. But then it leaves for a week and it comes back and they say it's stalled out. So back in the day, they were kind of patient with me. It came back like 3 times. And I would try a different thing and I'd do a different thing and I'd be like, yeah, I think it's good. So I put a new PCM in it, an ECM in it, and it came back again. So I was like, I got a problem with the crankshaft position sensor. It has a new sensor. The wiring I checked out, the voltage was good. I double checked it by checking resistance. The wiring is good. So what's that leave? Just the ECM. I put the ECM in it and it still came back. I'm like, I quit. I'm done. I give up. I don't know what to do. Maybe I'm not cut out for this. Sometimes these cars are a pain in the booty to fix. So I go to the foreman and I'm like, I don't know what's up with this car, whatever. And he said, whatever it is, we can fix it, but we got to have it act up. So instead of keep shipping it, I was like, look, we got to keep your car until it does it. And every day I'd drive the piece of crap around. And then finally, one day I went to start it and boom, it was just sha-na-na-na-na-na-na-na. And I'm like, all right, it's broken. Let me get the foreman. Help, help. And he's like, okay, oh, that Malibu's actually broken? Yep. So we go over there and this voltage was supposed to be 12 and it was like 5. And it was like, if you are supposed to get 12 volts here and you have 5, what would you guys think? Like resistance? Like what if we had a little resistance? Like maybe, would the resistance be here? Because I'm only worried about this sensor, so I thought it would have been here. Right? But then I thought about it. And even and the foreman guided me through this. Okay, so I'm gonna say like me and him, but it was mostly him. Okay, I'm just letting you know. But he was like, well, this has 5 volts, and it should have 12. That's no good. Check this sensor. He looked up in the diagram which sensors were on that bus, and this one had 5, and this one had 5. And then we kind of stopped. We're like, you know what? If they all have 5, we don't need to check 4 and 5. They're all gonna have 5. Do you think resistance right here would cause those ones down there to have 5? No, I agree. Don't you think it could be here? Yeah. I was obsessed with that. That's all I knew. That's all I understood. I was like, it's got to be resistance, but I checked it and I checked it and I checked it. And he's like, just pay attention. And I'm like, okay, okay. And you know what he starts doing? He disconnects this sensor. Then he disconnects this sensor. Then he disconnects this sensor and bang, all of a sudden it's 12 volts. And I'm like, what? Like they didn't teach me that in school, man. Why are you disconnecting sensors? And he's like, well, one of them's shorted. And I was like, no. If sensor 3 was shorted, it would like blow a fuse or something. No. This is a circuit where they make 12.0 volts through internal circuitry. And if something shorts it, it can actually just pull the voltage down. It won't blow a fuse. It won't catch anything on fire. It's just a reference circuit. It's not really high amps. It's just a circuit to be able to provide 12.0 volts to sensors. When he disconnected this one and it went up to 12 volts, he diagnosed it right then and there. And that was not in any service manual. And that was not in any of my classes. That was not in any of my stuff. And I was just like, how do I be like this guy? Like, how did you know to do that? He was just, you know what he told me? You don't need to know. No, he told me experience. Yeah. See, that was the difference. So engineers, sometimes I got a chip on my shoulder because they're like, oh, this is what we know and you don't need to know. And then this dude was like, oh, because I've seen this before. And he didn't make me feel stupid. And he didn't make me feel uneducated. He didn't make me feel like, you know, I wasn't good enough. It was more just like, dude, you don't know until you know. Like,
Yeah, now we show you.
and that's what I'm saying. So that made a pretty big impact on me. Was like, that was not in the service manual. That was not in the class. Like, all that was his experience. Now he showed me, and I'm going to show you. So now it's in the class, but you probably won't remember this all that well, except someday you'll have a problem like this and you'll be like, oh, that crazy guy talked about something like this. Okay, so when he disconnected it, boom, it came back up. So you know what the problem was? It was a totally unrelated sensor. It was actually a camshaft position sensor that would intermittently short internally, pull the whole bus down and make the car die. And the first code to set was just the crankshaft position sensor. And that was the only code that was setting. So that I was very fixated on that. But come to find out, it was actually down here at the camshaft position sensor. That sensor was like 20 bucks. And it was right there. And I put a new crankshaft position sensor And I checked the harnesses extensively and I put a new ECM in there and none of that was the problem at all. I totally misdiagnosed that car like in 3 different ways. The cool thing was back then the customer wasn't looking to sue that much, but now honestly, if you misdiagnose a car several times, it's under warranty. They're going to get lemon law. They can be bought back and paid back and pain and suffering. And or if that car were to stall in an intersection, what could happen? You get an accident and then they're like trying to sue your dealership for millions. You see what I'm saying? So like, this is a harsh environment, a harsher environment than it was for me. That misdiagnosis was probably like 2008. And things were a little different back then. They weren't amazing, but they were different. People weren't quite so lawsuit quick, you know, so I tried and tried. I mean, he wasn't paying for each repair. The dealer was like, no charge, we screwed up, you know, but at least he didn't also try to sue in addition to get free stuff. Makes sense? So that one hurt me a little bit. And that's why I like to include this on the in the lecture. So, you know, if all these sensors share one bus, you can have issues with that bus. Cool. So pretty good one. Now let's erase all. Okay. We'll put this away for a little bit. And then as we get into some other types of sensors, like, for example, well, these ones are switches, right? So this one is kind of cool. If this one is the park neutral switch, what really happens here is we've got 12 volts coming in from the fuse. This is a good one to cover as well. 12 volts, we'll do red coming in, right? All right, if it's in low, it's going there. Actually, no, this is park. This is reverse. See this? Park, reverse, neutral, drive. If it's in park, we've got it going down this way. What's the voltage going to be on P? It should be 12, exactly. So again, they'll put a little sense circuit in here, and that's how they'll know if it's in park or not, right? But what if we have 0 on the sense circuit? We know it's not in park. What if we have 12 on R? We know it's in reverse. What if we have 12 on D? We know it's in drive. What if we had 12 on N? That would be neutral. It'll actually allow it to start in park or neutral, but that circuitry is inside here. So as long as it's getting 12 on neutral or 12 on park, it'll let it crank. But this is how it gives position to the ECM to let you know what position your shifter's in. Okay, so kind of fun. Then as a result, when you go to turn the key on an older car, you were closing a relay and sending voltage out to the starter. On a more modern vehicle with so many things, you're turning a key and the key is more like giving a signal to the ECM, and the ECM's gonna be like, do I want to crank it? Yes or no. And if it decides it does yes, because it sees the right inputs, then it will actually send voltage out to the starter relay. Okay, so a lot of our diagnosis is going to be at these terminals of the ECM right here. This. So time and time again, as we continue, you're going to be like, oh, we're testing the terminals at the ECU again. You just got to know what's supposed to be on them. All right, pretty good. Then we talk about like temperature sensor operation. I showed you the voltage divider circuit, but what I have to make sure you understand is electrically what's going on is this sensor is going to change resistance with temperature. So if you recall what that looked like, that was a variable resistor. It looked like this. See this symbol right here? That's a variable resistor. So if we're actually working with something like that, it could be, let's make it a engine coolant temperature. How about that? The engine coolant temperature is going to be submerged in the coolant. The resistance of this sensor is going to go up or down depending on the temperature. And I showed you that inside the ECM, it's going to do like a 5-volt reference. It's going to go through a fixed resistor, and then that's a voltage divider with this one. If they were the same, we would have 2.5 volts on the sense wire. But what's really happening here is, let's say, if our resistance goes up, high resistance means low temperature. All right, so with most things in nature, the higher the temperature is, the higher the resistance is. Like if you get a wire and you heat it up, the resistance goes up. Then they found some other materials, kind of like freaks of nature in a way, where if you heat it up, the resistance goes down. It's a thermistor. It's an NTC thermistor. And you're like, whoa. Well, they take that material and they build it into the sensor. So that way it reads really accurately. It's very linear. It's very precise. If your coolant is high resistance, that's going to be because, oh, this one is actually a PTC. Low resistance. Low temperature. I actually think I worded that backwards. Let me get my mind back on. Low temperature. No, this one's, we'll go with this, but they could be NTC or PTC. So I'm going to explain just how it was. If you have a low temperature, you're going to have a very high resistance. If you have a very high temperature, you're going to have a very low resistance. All right. But if you have a very high resistance, you're going to actually get a very high voltage. And that seems kind of weird. Your ECU doesn't measure resistance. It really measures the voltage. So remember how it had that sense circuit right here where the red wire is? Well, if your sensor is, let's say, it's really, really cold, that means the resistance is going to be really, really high. If your resistance is really high, this is going to consume more of the $5, right? 5 volts. This is a very strong sibling. So it's going to be like, you know what? I'm going to take like $4.70 and I'm going to leave this fixed resistor with just 30 cents. Make sense? Get it? All right. So if this sensor has a lot of resistance, it means it's really low. But what the ECU is really doing is it's monitoring the voltage. So when you follow the troubleshooting chart, a lot of times it tells you to check the voltage. And you're like, why am I checking the voltage? Why don't I measure resistance? Well, you can. If you want to measure resistance, you can do that. You could actually take the sensor and put it in a pot of water and get it up to a certain temperature, measure with your thermometer, and that should transfer to resistance. So if you look at this, let's say that your coolant was 100 degrees. If you draw this up, that should be like 0.8 0.8 kilo ohms, so 800 ohms. That would be equivalent to like 9 volts if it was in the circuit. That's a great way to be accurate, but how much time do you think that's going to take?
A lot.
Yeah, you're going to be like, hey, let me diagnose your check engine light. First, I need to drain your coolant. Then I need to take your temperature sensor out. Then I need to go home and boil some water and put a thermometer in it. And then I'm going to do some experiments on this one particular sensor and then be like, how long is this going to take? Because I was hoping to have it diagnosed in an hour or less. Make sense? So this is visually makes a lot of sense. Practically, what we're really going to do is send out a reference voltage. This is a fixed sensor. This resistor varies. We're going to see what the voltage is there. So if it's 100 degrees, you can expect to have like maybe a 0.8 volts. But if it gets really hot to like 212, you're going to get like a 4.5 volts, right? So you can look at this chart and be like, let me measure at this point right here, because that's what the ECM does. You measuring the voltage is a more accurate, dynamic way to determine the resistance without having to take it apart and measure it and do experiments on it, right? So the ECM is actually watching this voltage because this resistor is going to consume some and this is going to consume some. Okay, kind of makes sense? Now here's the range. As low as it went, you can see it goes down to like about 0.3 volts, maybe even 0.2 volts. And as high as it goes, about like 4.3. So let's make it an even number. Let's make it a 0.5 to a 4.5. That's the normal range of a sensor. At 0.5, that thing's going to be like really, really, let's see, if we follow this, and this is the graph, that's going to be like really hot, okay? But if it's at 4.5, and then you follow that down, right, because this is the range, 4.5, that's going to be like really cold. The coldest it'll get typically is like -40. That's the range of the sensor. It can read as low as -40. What if it's colder than -40? I'm sorry for you. There are places. There are places. If it's colder than -40, this sensor can't tell. It can only see so low. But what if the temperature, as high as it can go, as you can see, is potentially maybe like 240, 248? Should it ever be over that?
No.
Shouldn't be. If it is, you got a big problem. It can't see beyond those readings. So if you had, let's say, a rodent chew a wire right there, let's think about what that would do to the circuit. If a rodent chewed this wire and you had an open right here, what do you think your voltage is going to be reading? All right. Will it though? Because look, this is the resistor, right? Voltage goes through this, and then it's like, and then it's going to go to this point. So it would read super high. If this was 5 volts and you had a full-on open, you're going to have 5 volts right here. So if you had a full 5 volts, that's going to tell you what's the temperature. It's going to tell you like, well, this one's a little bit backwards from what I would normally do, but it's going to tell you temperature way on the extreme. Like typically, if you have a 5 volts right there, it's open, it's going to read like -40, but also you're going to get a code. Because remember, the range is a 0.5 to a 4.5. As cold as it gets, it could go as low as 4.5, and as warm as it gets, it can go as high as 4.5. But if it's higher than that or lower than that, you know what the ECM knows? There's an open, there's a fault, there's something wrong. That's how you get the code, right? But if you just had a little bit of resistance right there, you might not even get the code. As long as it lands between 0.5 and 4.5, you won't get a code. It would just be reading the wrong temperature, which could make it run bad, fail smog, poor fuel economy, right? So in that case, you'd have to actually start to like measure your coolant temperature with an infrared temperature gun and then compare it to what the sensor's reading on the scan tool maybe, right? It can get kind of tricky. All right, but let's just say we had an open down here. This one goes to the ground. That's kind of interesting. So if we had an open ground, that would still give us 5 volts. Let me think. Full voltage, it's going to go to there, it's going to go there. Yeah. What if we had an open right here? Then it would be 0, and 0 volts is going to indicate super, super hot, at least on this. This is a PTC thermistor. Normally I do NTC. I think NTC because they're more common. But if it was an open, that would read super hot. Now, if it was a PTC, it would actually be a graph like in the opposite direction, which I didn't catch. I looked at that and it looked pretty good, and I was like, yep, I'm gonna use that one. But normally it would be one more like this, right? Something like that. Well, I made it worse. You draw with the mouse and let's see how you do. It would look like this. We'll just call it like that. So if you had like really, really high voltage, that would mean super high temperature. But if you had 0 volts, like let's say you had this one, it'd be low temperature, So it depends on the exact type, but electrically, that's how that temperature sensor is going to work. All right. What if we had a sample question? So this one's something I'm going to talk you through. I want to see if you can figure it out before I explain how it works. Okay, so I'm switching it up. A vehicle is being diagnosed for a stored throttle position sensor circuit range performance. DMM is connected between X and ground. Technician observes a reading of 0.75 volts. All right, let's draw that in. X and ground. X will do, pull it down here. Let's make our meter black. How many volts? 0.75. Super hard to draw with the mouse, let me tell you. All right, and where was the ground connected? So this is saying connected between X and ground. So it's saying ground like this. It's its own ground. When it says ground, it means like the chassis ground, like its own ground. Okay, and we had a reading of 0.75. Okay. Which of these could be the cause? Okay, this is, well, I gave you the answer, I forgot. But if you look at this, let me draw how this should work. Do you see this? What's that? So this should be ground, right? All right, that should all be ground. And even technically ground should go all the way to here, because what's this thing? That's the load, which means then this 5 volts should go all the way over here. So let's predict what voltages we should have. And I think this is pretty doable for you. How many volts should we have on W? 5 volts. Yes, you're getting there. How many volts should we have on X? 0. What do we have? So we have like 0.75 too much. How many volts should we have on Y? 0. Okay. Now, what if we were to have 0 on Y but 0.75 on X? What's that tell you? The wire shouldn't be consuming voltage, right? So if you have 0.75 here and 0 here, the problem is between here and here. That would be the wire. But what if we had, yeah, exactly, high resistance in the wire. But what if we had a 0.75 here on Y? We should be all the way down to 0 there, right? That would mean you have resistance somewhere between here and here. All right. And on Z, we'll come back to Z, okay? But for now, 5 volts to the load to ground, that's pretty much what we're looking at. So if we were to look at those readings and be like 75, you can already tell you got something going on with the ground, right? There shouldn't be 0.75 left over. So let's see what we got for X. Nothing, doesn't really talk about X. Let's see what we got for Y. What's that say?
High resistance.
Hey, doesn't that answer that for you? We got high resistance at Y. What is Y? Well, I don't exactly know. Let's say Y is a male terminal going into a female terminal, and there's corrosion here from water intrusion. That would be resistance. That would leave 0.75 volts right there, because it would be dropping the 0.75 on this connection. Make sense? So this wouldn't drop the full 5. It would save 0.75 because it's like, hey, we got to pay another toll up ahead because there's unwanted resistance. Make sense? Okay, cool. But let me explain this just a bit more. This wire right here has a range of about, you're going to get used to this number, 0.5 to a 4.5. And the reason why is this is going to sweep. If you're way up here, that's going to give you like a 4.5, because look, it comes out as 5 volts. It goes through just a little bit of resistor. This drops 4.5 over the whole length. If you're in the middle, it'll be at like a 2.5. But if this is swept up to the top, you only drop a little bit. You'd probably get the 4.5 number. But if this were to be down here, you'd probably get like the 0.5 number. Make sense? This is literally a resistor, and this is a contactor, and it's going to actually make contact at different positions. When you start with 0 throttle, you're right about here. When you go to half throttle, you're right here. What should your voltage be at Z? At half. Exactly, at half, exactly. Then what about at wide open way down here? 0.5. All right. What if a two-legged varmint, I tell you, rips, let's say this cuts this. Now how many volts do we have here? 0. So you know what we're going to have at Z? 0. You know what you're going to have? A DTC. Make sense? You're going to have a DTC because the normal range is 0.5 to 4.5. It should never have a 0.0. If it has 0.0, it knows something's up with the circuit. That's why you'll get a code like this. What if we were to have an open right here? What if we fix that top open and we had to open down here? You'd have 5 volts. You'd have 5 volts. 5 volts would come all the way to here, right? So what voltage, if we have 5 volts going all the way to here, that means you're going to have 5 volts going all the way to here. That means your sensor is not going to read 0.5 to 4.5. What's it going to read? You've also got a code for that. So that would be a high voltage, or a 0.0 is going to be a low voltage. What could cause the high voltage? An open ground. Pretty much that's about it. What could cause the low voltage? An open 5 volts, or an open sensor, or this wire being open could also cause it, because Z is what we measure. The ECM actually measures it back here. So if we have an open right here, this would read 0, you'd get a low voltage code. So again, you got a throttle position, sensor, circuit range, and performance, and AutoZone's like, oh, you need a throttle position sensor. And I'm like, are you sure? Because I'm going to say that it could be the sensor. I agree. Because we could have an open here, 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 all the sensor. But couldn't it also be this wire? Could it also be this wire? Couldn't it also be this wire? Couldn't it also be right here? That's an ECU. Couldn't it be right here? That's an ECU. Couldn't it be right here? That's an ECU, right? It could be the ECU, it could be the wires, or it could be the sensor. So to AutoZone, I say you're fired. Because that's how it is. Like you don't know what you got, right? So that's a good ASE one. And here's how that would look more as part of the lesson, which I kind of prematurely jumped the gun. This is showing you what you got. This is going to give you a voltage. That's a voltage constant, 5 volts. Depending on the position of your throttle, because when you push the gas pedal, you move it, right? That literally moves this lever, and that sweeps against this variable resistor, and that'll give you a different number. And then this one is always going to be ground, right? So you got 5 volts, you got ground, and then this one is going to give you a varying voltage to indicate throttle. If I said 2.5 volts, what's that tell me the throttle position is? Halfway, yeah, exactly. If I say 0.0 volts, that's out of range though. If you're at idle, it should be about 0.5. Maybe 0.3, not 0.0. They always make it so that there's these outlying numbers that would help it diagnose itself by setting a code, okay? That's really how it works. Okay, this system right here is old school. I like it. It's a good teaching tool. This system right here had problems where this, let's say that most of the time you're riding around 20% throttle, 10 to 20%. You would wipe this back and forth so many times. You know what it would do? It would kill the resistor right there and wear it out. And then you'd have a dead spot in your throttle. So if you were to be throttling and it was good, and then when you hit 10%, your throttle drops right off. And then at 20, it picks back up. You probably wiped the resistor off right there. So they took that and they were like, hey, these aren't that reliable. They're cheap and they're easy to diagnose. And they went to something more complicated like this. So this one here, we're going to have to spend a little bit more time on, but not today. This one is going to use Hall effect chips, and it's going to be multiple positions. And this Hall effect chip is going to measure position 1, and this Hall effect chip is going to measure position 2, and they're going to be a double redundancy. So remember we were talking about over in the lab how the customer claimed the electronic throttle system failed and accelerated out of nowhere? Like, I doubt it, because you have double redundancy on this Hall effect chip, and these are reliable anyway. And for the two of them to fail at the same time in the same moment, I don't think so.
No, it's not rare.
I just don't think it's going to happen. It's just not likely. Right? So then again, when you look at this, closed throttle, 0 volts, wide open throttle, closer to 5, but never all the way 0 and never all the way 5. That's kind of what this is saying with a single contact. They do also have them to be more reliable with a double, and it's an actual contact type. So when you have 2, it's kind of like this. They'll give 5 volts once. They'll give ground once, but to both of them, right? And then essentially you have VTA, which is the variable, 0.5 to 4.5, and then 0.5 to 4.5 again. But this resistance is different. So it'll have this resistance, VTA, is like starts at 0, but it's really going to engage around like 0.5. VTA2 is going to start more like 0.1, and actual reading is going to be more like, or 1.0, and the actual reading's probably going to be more like a 1.5. So if you had a 1.5 on VTA2, and a 0.5 on VTA, you'd be like, yeah, that's a legit number. But if you had a 1.5 on VTA2 and a 3.5 on VTA, it'd be like, nah, those don't correlate. Do you want to know what the system will do? Limp home. If those at any point disagree, limp home mode. It's just gonna be like, no throttle, we're not sure what's up. You get these codes, throttle position 1 and throttle position 2 correlation, and then you got to go in there and actually measure which of them seems correct and which of them seems incorrect, which is generally going to be in the sensor itself. But there's always a possibility it could be in this wire, which would be a harness repair, or this wire, which would be a harness repair, or in the ECM, which is going to be an ECM, or in the ECM, which is going to be ECM, right? So that's very, very electrical and kind of complex, but I think you guys will understand it. All right, then we have similar but non-contact. So again, this is going to work really the same, but internally, there's Hall effect chips. There's nothing to wear. There's no wiping across the resistor to wear it out. It's non-contacting. It's a little complicated to explain, but we will when we cover sensors. And then let's say you wanted to check that TPS. I would suggest doing it by checking voltage like this. But if you're ever a little bit confused, you could check resistance like this. And you could be like, all right, at closed throttle, it should have like a lot of resistance. And at open throttle, it should have like a little resistance. And you can sweep it. This would be what's called a throttle sweep. So you look at the number, and what would you do to change this number? Push the gas pedal, let the gas do a sweep and make sure it moves really smooth. But at that point, you got to watch your meter really carefully and be like, all right, 1 ohm, 2 ohm, 3 ohm, 4 ohm, 10 ohm, 20 ohm, 30 ohm, 50 ohm, right? Like, don't you think it might make more sense to graph that?
Then you can just see it over time.
Exactly. So just keep this in mind, because so far we've been all about the meter, right? Pretty soon we're going to be more like, hey, let's talk about the oscilloscope. Cool. All right, here's another one. Talking about your meter. What the heck is that number? Who knows how to do this? All right, 0.002 kilo ohms. This is a literal ASE test question. Sample. They'll have questions like this. They'll be like, the reading shown above is observed while checking resistance of a temperature sensor. What does it indicate? 2 ohms, 200 ohms, 2,000 ohms, or 20,000 ohms? And you're like, it doesn't. It's 0.002. Yeah, but it's kilo ohms though. What's a kilo mean? Oh, yeah. 1,000. Okay, so let's think about that. If it's 0.002, the way that I do these is this. I've showed some of you this. Okay. Kids have dropped over dead converting metrics. You don't have to really understand this if you don't want to, but at a minimum, this is a little m, by the way. So I should actually redraw that as like a lowercase m. All right, that's a milli. That's nothing. And that's kilo. So if we have 0.002 kilo, let's do it like this, kilo, but the answers are in ohms, we need to go this way. How many times? Kids have dropped 3 times. Okay, so it's actually how many ohms? 2 ohms. That's correct. The other way you could think about it is, now I don't know why you'd know about this, but if it was grams, let's just say that you were moving grams of widgets. If you're moving grams of widgets and you have 2 grams of widgets, you think that's similar to a kilogram? If you're moving kilograms of widgets, you're in big business, am I right? So if you had 2 grams and I said, no, I have 2 kilograms of widgets, you'd be like, whoa, 2 kilograms? Like, these are way different numbers. There's 1,000 grams in a kilogram. Does that make sense? So that'd be the way to look at this. If you're like, oh, there's 0.002 kilograms, how many grams is that? You just remember it's on 1,000, right? Actual grams, that's going to be like 2 grams. Okay, but you have to remember it's 3 digits. From kilo to grams is 3 digits. The reason I do it like this is because I don't remember which way to go. But when I draw it out like this, I know which way to go. I'm at kilo and I want to go over to no prefix. I go to the right 3 times. You could always try to go both ways and be like 0.002, like it's not 200,000 grams. Cool. Okay, what if you're having 2 milligrams? What's that mean to grams? Do you know? Well, milligrams over here. So if you want to know how many grams that is, you got to do this. 3 to the left. 2, it's 2.0. 1, 2, 3 is like 0.002 grams. So that would be 0.002 grams. We're not going to call it, we're not going to say, hey, I need aspirin. Do you have 0.002 grams? You're not going to say that. You're going to be like, do you have 2 milligrams of aspirin? Makes sense. When you're talking a different unit, that's how you're going to do it. Okay, so if you were to look at this, you could say, let's make it 2 ohms. How many kiloohms is that? 1, 2, 3. 1, 2, 3. That's 0.002 kilograms. I mean kiloohms. And then if we were to go to milliohms, that would be 2. 1, 2, 3. That'd be 2,000 milliohms. Okay. I'm just going to let you know there's going to be an ASE question about converting metrics. There just always is. It's not that hard. Okay. You think you can do it? Well, if you can or you can't, you still need to. And sometimes the specs are one way or the other, and you can always change the meter to match the spec, but it's good to be able to do the math too. Now we'll talk just a little bit about some other sensors, and we, in 24 minutes, we'll go on our break. Okay, you got this. You can do it. All right. Anybody ever heard of a mass airflow sensor? Yes, you have. Mass airflow sensor is going to be a lot more complicated to understand, so we'll cover it independently. But for now, I'll just say the mass airflow sensor has several wires going in, and it does some things with the hot wire, and it's going to cool the hot wire depending on how much air comes in. And the more air that comes in, the more it's going to cool it. So it's going to have to increase either the voltage or the amperage or both. And so we're measuring the volume of air based on how much electrical flow we're sending through that resistor to keep it at the same temperature, right? That's the overview. Where we can apply it to electrical is right here. If you had a problem with a mass airflow sensor, it could be the sensor, but now let me see if you've been paying attention. It could be the sensor, but what could it also be? The wiring or? Exactly. So how would we know? We're like, oh, we got a code. All right, well, here's a cool connector end view. I don't know exactly what it should have on each of these. So I could look at the connector end. That's the end view. Then I could look at the diagram and be like, all right, let me figure it out. So I'd say, if I were to look at this, I'd start with what's red. And I'd say, okay, we're pretty much having the battery. It's going to go through the EFI main. And that's going to actually, EFI number 2 is going to actually provide something to the mass airflow. What do you think that is? B+. What's that going to be? Source, right? 12 point something. So what should I have at this terminal right here? Bingo. Make sense? And if you don't, you're going to put a mass airflow sensor in it? No, then you're going to have to find out why, maybe that fuse, maybe that wire, maybe this, right? So again, you'll see the diagnosis is very electrical. And let's just say if we have 12 volts on the B+, what do you think we should have? And this one you may not know, but it's okay. What do you think we should have on the E2G? Oops. E2G, I can tell you just because I know, is going to be a ground. How do I know? Well, I know because I remember. But if you didn't know, you would actually go in and look at the connector end views, and it's going to give you the E2G. E2G, I think, is going to be the ground. Actually, you know what? It may not be. It may be the VG. I think VG may be ground. I might actually have to look into that one. Yeah, no, E2G is the ground. All right, so that one should have ground. How would I verify that? Look at this, E2G. Exactly. I would move my meter over to here and it should read 0.0, right? And if it doesn't, then I know I got to troubleshoot something with this. It could be the wire or it could be the ECM. If I had right here, let's say I had 2 volts there, what do you think the problem is?
Bad ground.
It's a bad ground, but we don't know if it's the wire or the ECM, huh? So what if I move my meter over here and I still had 2 volts? Yeah, it's not the wire, it's the ECM, exactly. But what if I moved it over here and I got 0 volts over here? Then it's the wire. Boom, there you go. If you can understand that and you can measure that, you can fix stuff legitimately. Ah, yep, very possibly, exactly. That's why I use those examples. All right, so that one should have ground. Then what do you think all is going on over here at VG? Because we haven't covered this type of sensor yet, so I gotta like kind of fill you in. VG is gonna have a varying voltage. I don't know exactly what the range of that sensor is. I would have to look it up. And when I'm gonna test it, I could say like, hey, what should it have? And let's maybe say it has like 2 to 4 volts. And if it has 2 volts over here, but then I check it over here and it has 0 volts, that would indicate this VG wire is open. But if it has 2 here and it has 2 here, then be like, nah, the wire's good. I just have to know if the 2 is good or not. And this is where it goes away from electrical. At this point, you have to look at a chart and see how many grams per second of air and compare it to a chart and stuff. It gets kind of complicated. So pretty quickly, it's more engine performance. So we'll pause on that. But at least you got to make sure the sensor has what it needs. It needs 12 volts here. It needs ground here. And then it's going to generate a signal on VG. And then whatever that signal is can't be lost on the VG wire to the ECM. But to determine what exactly should be on VG, we're not quite there yet. Cool. And then similar with the intake air temperature, this is that one that puts out a 5-volt reference. And some of it's going to be dropped here and some of it's going to be dropped here. But depending on what the resistance is there, that'll tell us how much we should have on a sense circuit. So again, that's just a temperature sensor. So if you electrically know how to diagnose these types of sensors, you can. The reason that this connector has so many wires is because it's a mass airflow and an intake air temperature all in one. Okay, so there's 2 sensors you could diagnose on one connector, but if you only have a problem with the mass airflow, you don't really necessarily need to test the intake air. You're only worried about these wires right here. All right, pretty good. Very nice. What if, and this is just a little overview of the types of sensors, okay? Not every sensor will be covered. What if we have a AC frequency type sensor? Here's a little bit of the mechanics, and we'll do the electronics. There's something spinning, and when it spins, every time one of these points comes by this coil, it's going to give us a little pulse. And then if it's passing, this point is going to get further away. That's going to kind of give us like a less of a pulse. But then this next pulse is going to come in, right? So right here, when we were on our way up, that was because this point was getting closer to that magnet, that core. Then when it passed, it peaks when it's right there. Then when it passes it, it starts to go down. Then when it gets as far away as it can, the next one starts to get close, so it starts to come back up. Can you kind of visualize that? So if this is point 1, 2, 3, and 4, this is 1, this is 2, this is 3, this is 4. We're back to 1, 2, 3, and 4. So the way this works is because this is magnetic, every time this magnet is going to go by this core, it's going to induce an AC voltage and current into that coil of wire. The closer it is, the more it's going to induce. the further it is, the less it's going to induce, right? So this thing would be spinning. If this is spinning, it's going to generate it. If you wanted to test it, you could actually go to this wire, maybe right here, and measure the AC voltage that's in that wire. What should the AC voltage be? Can you tell? It depends on the position of the moving part. That's the problem. So you could put your meter on there and you could be like, oh, it has, and then the meter is going to be kind of jumping all over the place and it's going to give you kind of an average and you'd be like, what the heck? Like, I don't know what that is. So we can use the meter. I sometimes do use the meter, but do you see how this is graphed? Well, later you'll see the meter doesn't really graph. That's not the meter's thing. And we're going to have to get the picoscope out or the oscilloscope out to really graph this. But let's just say you measured here and you had that type of a graph. But then you measured here and you had a flat line. What do you think the problem is? You had a good waveform. We'll call this a waveform here, okay? You had a good waveform here, but then right here you have a flat 0 volts. An open where? In the wire. Yeah, again, you see how so electrical this could be? If you have a good signal here, that same signal should be available here. But if the signal's available here and it's lost in here and it's not available here, then it's the wire. It doesn't have anything to do with the sensor itself. Makes sense? But if the sensor is no good and you get no good waveform here, there's obviously not going to be a good waveform here. Then it'd more be like, I don't know, let me see what's up with the sensor. Maybe the sensor's not getting what it needs. Maybe the sensor's no good, etc. Right? So that's kind of what this is saying. And if it's DC, it's going to be kind of the same. Rather than this waveform, peaks and valleys, it's going to be square wave waveforms, right? So if you had the VC is the reference voltage to the sensor. If this was a flat line at 0 volts, I'd see if VC is making it to the sensor. Make sense? But if you had a flat line at 5 volts, I'd see if VV1 had a ground, right? So it's kind of similar to that TPS. If you lose the voltage reference, it'll read 0 volts. If you lose the ground, it'll read 5 volts. Then you could go with this and you could actually try to measure the voltage on the VV1 plus, and it's going to be like hard to do on a meter. So you're going to probably go to an oscilloscope and you're going to get a waveform. But if you had a good waveform right here, and then over here you lost the waveform, that would tell you with good assurity it's in the wire. But if it never made a good waveform at the sensor, you know you got something else going on. You could check the 5 volts, you could check the ground, and if it's still not making it, it could be the sensor, but it could technically also be inside, like the timing rotor, maybe got broken off or something mechanical too. So without making it too mechanical, we'll keep it. Then you can kind of see, here's your digital. Digital is just going to speed up. AC is going to speed up, but it's also probably going to start making higher and lower voltage with speed. They generate more on an AC. So these are both normal. And what they could look like would be like this. So that could be bolted in the engine. When you go to test it, you could make sure that it's getting what it needs. But then after that, really quickly, you're going to want something like this. So have you ever seen a DMM give you these? It doesn't. If you want to test these types of sensors, you need to go to a different type of tool, right? And so if we were to say, try to test this, we could make sure it's getting the 5 volts in the ground. But if you're actually going to test the signal, this is going to give you a more thorough story rather than a voltage changing on your meter, but you're not sure if it's a good form or not. For example, look at this. Can you guys tell these teeth are square? What happened to that tooth? Two-legged varmint. Yeah, somebody chipped it. What do you think? Your meter wouldn't catch this, so you know. What do you think would show up if you did a full-blown oscilloscope like this?
You see like
One of these would look chipped. Literally, one of those, each of those peaks are teeth. So you'd see a bunch of them peak, and then one of them would come down, like wouldn't go the whole way. This is actually not it. This is a double space that they put on there just to identify the location. But one of those one of those waveforms would be a little short. It'd be like tall mountains, and then one would be like, oh, that mountain's kind of sad, and then tall mountains, because that one's chipped, it's broke off. So again, I'm more making the point that when you get into these types of sensors, your meter's not going to do it when you're really trying to evaluate it. But if it was like this, you could. So here's a Hall effect sensor. That's a speed sensor. Vehicle's being diagnosed for a crank no start complaint. Technician connects the DMM to the circuit shown, observes the reading on the meter during cranking. Okay. B plus, what do you think should be there? Battery, 12 volts, which should go to the Hall effect sensor, 12 volts. What do you think should be here? Ground, which would go over to the sensor and be ground. But remember, this signal, to really see what's up with that signal, you really want to put that on the oscilloscope and graph it and look at it. You want it to look like maybe this, or like this, or like this, or like this, depending on what it calls for, depending on the design of the teeth, right? So see how there's teeth and teeth and teeth and then no teeth? It's going to look like this, right? Or if it's ASE, it's going to look like that. That is on the flywheel, yeah. Yep. That's how it's telling crankshaft position. Sometimes they put it back there. All right, but in this case, we don't have a meter. So we don't have the oscilloscope, we're using the meter. So the meter is not a great tool for this. However, what's this meter reading? All right. Do you think we should have 12.6 on the signal? Because I showed you the signal should look like these. Does that look like 12.6? 12.6 would be a steady line way up here. It should be pulsing something. Exactly what pulse, I really don't know. But I know it shouldn't be reading 12.6 steady. That's showing it has no pulsing. What could cause no pulsing? Well, let's see. Maybe a damaged reluctor, but if it was a chipped tooth, it wouldn't cause 12.6, right? So if it's a little bit damaged, maybe. If it was so damaged that it broke off and it was laying in the bottom of an oil pan, maybe. But I still actually don't think it would cause 12.6, though. It would probably cause 0.0. What about an open B plus? No, because how do you think it got the 12.6 in the first place? The B plus was given to the Hall effect sensor. If it had no B plus, it would have never even been able to produce 12.6. What about an open in the signal wire? Right, because this gives B plus, this gives ground, and this should be giving a pulse. The fact that it's giving a steady means like this sensor is not working, right? This would not be the best way to diagnose it, but this was a sample question, and it's technically accurate. So if you really want to diagnose it, what do you think you got to do? You see this thing? This is a waveform from a picoscope. The picoscope is a computer-based scope, okay? So I'll give you a run-through of DMM versus pico versus oscilloscope, which is like a DSO, okay? A pretty basic one. I like the pico because, well, let's just say an oscilloscope in general. It's going to replace the numbers as seen on a DMM with a picture, all right? So you see this blue line on your meter, you wouldn't even be able to comprehend that. It'd just be like, oh, it was 5 volts, and then it was 0 volts, and then it was 12 volts, and then it kind of sloped down. You're like, you wouldn't even know, you could never observe that really. So when you put it on an oscilloscope, you're going to graph it, and the graph is going to tell you so much more, right? So like back here, when we were looking at these sensors, this is going to tell me everything I need to know. If it's got a broken tooth, I'm going to see it. This is a screen from an oscilloscope. So you could use the meter to do some things, right? But once you want to get more advanced, you need to change over the oscilloscope. The oscilloscope, very simple. This is voltage over here. See this? That's voltage. Do you know what this is? Time. So what if your voltage was, let's just say, let's say your voltage was 12 volts. Let's say you looked at your meter and it went 12 volts, 0 volts, 12 volts, 0 volts, 12. On your meter, you could kind of see that, but on this, it's graph it. It'd be like 12 volts here, then just after it was 0, then just after it was 12, and then just after it was 0, and then it was 12. You could literally see what the voltage has done. It just graphs it. It graphs it for you so you can understand it. Now, that's going to be especially critical when you get into some of these more challenging, different sensors that you really want to graph, right? So here's a standalone oscilloscope. Here's another one from OTC. These have their own screens. They're kind of nice because they're more portable and they're pretty heavy duty. The negative is these are very manual. You got to set these up. This is a Pico. This is going to be the preferred, and we'll do that. The Pico, you connect to your computer. So does this look kind of old?
Yes.
Would you use a 10-year-old laptop? That thing is in the trash. Kind of similar with Picos, right? The Picos, the old ones were slow and the new ones are fast. Well, this is just the Picos. This is just the oscilloscope box. If you get a new computer, you get all the new speed improvements of your new computer, and you can still plug in this Pico, and the computer is doing the processing, so it'll speed your oscilloscope up. Whereas this one, you get a new computer, it's separate from that oscilloscope, so your oscilloscope's still an old piece of crap. I don't really like oscilloscopes that are standalone, but there is a time and place for them. I'd prefer a Pico for several reasons, mainly because they don't really age out. It could be a 20-year-old Pico box, and you get a brand new PC, and that thing's a beast because it's just the box. Make sense? So as we look, if you were to look at analog versus digital storage, analog scopes, in fact, I'm going to skip to the picture because this will summarize it for you. You'll laugh. All right, an analog scope looked like this. This thing is 3 feet wide by 2 feet deep, and you roll it into the corner of the shop, and it has all these leads hanging off it, and when you're done with it, you just let it die in there. You just roll it in the corner and let it die. You saw it at high school, didn't you?
Yeah, and I think we have one in.
We probably have one hidden over there covered in dust in the storage container. Yes, I admit. This was an analog scope. It was effective. You could graph it and stuff like that, but you would do it and it was gone. Whereas if you start to do like a digital, like we were back here, if you have a digital, that's going to be able to do it's going to be able to store it and save it. So see this? You could take it on a test drive. You can actually record it in Zoom. A lot of times it's a very powerful automotive software. So that old machine, that analog one, there was no software. That was just a measuring device, and that was it. And they were cool back in the day. But they also can have like pressure transducers, different sensors. There's tons of accessories. We could spend, honestly, I swear, like 3 days on Pico, but we won't. All right, so I'll just get you kind of familiar. Now, when we do these tests, we're going to end up with a waveform. Do you know what the waveform is now? This is a waveform.
Yeah.
This is a waveform. This is a waveform. You know what's cool when it's a digital, or even better, like a Pico? There's storage libraries of known good signals. So how do you know if that sensor is good? You can get your own waveform, and then you could compare it to a known good one that's in the software and be like, hey, we got the car when it was brand new. We took all these picoscope readings. These are all what they should be. And then you could look at yours and be like, wait a minute, mine's messed up. I found the problem, right? So again, there's no reason to go manual. And you can save them, and even say for future analysis or reference, you want to know what I would really sell? You can send this to like a manufacturer specialist or an engineer. If you're trying to fix something unfixable, like what I shared with you the other day, if I got a waveform and I could send it to someone in Japan and they could look at my waveform, now you can really fix some stuff. Make sense? But if you got like your meter reading, you can't really, there's no way to share that. If you have an analog reading, there's no way to share that. This can actually save a snapshot, and you can send it in a file, and they can open it and they can replay it on their computer. So this is just the preferred way, right? So here's some various waveforms. That's a digital storage. Sometimes they can record, but within themselves. This thing can't send an email. The Picoscope can because it's plugged into your computer, right? And then once in a while too, like if you were to look at, depending on the sampling rate, if you had a fast sampling rate, see how this goes up and down a lot? If you have a slow old piece of junk, it samples so rarely, it might give you a waveform that's missing microsecond defects. Make sense? You want something that samples really fast so you can see all the changes. If it's slow, you're kind of taking the average. If it's a meter, it's literally taking the average. And sometimes when they take samples, they'll do this interpolation where they'll either curve it or they'll just make it straight. It kind of, if the sample speed is fast enough, it doesn't really matter. But if it's slow, it's a big problem. Cool. So this talks a lot about sample speed. You want the fastest you can. This is old, horrible sample speed. This is newer, better. But if it were me, I would just go with the Pico because it's as fast as your brand new computer. Cool. So overall, I think that was the main thing was good. This is a normal waveform. If you had one with a broken tooth, you'd see it and you could compare it, right? There'd be a gap right there. This is the Pico, so this is my main plug. Your brand new computer with the existing 20-year-old Picoscope is just as fast as your brand new computer. So this is what we'll be practicing with a little later. And again, the justification is with these sensors where we need a waveform. And then some of the scan tools actually have a built-in Pico as well. This is different than if you have a graphing scan tool that graphs your live data. It's different than an actual Picoscope. If it's a Picoscope, you're going to actually have to make probes. If you're taking it off the DLC, that's not a Picoscope. That's just graphing data. If you had to actually look up the wiring and look up the probes, like remember how we were way back here, and you're talking about how we would go ahead and we could probe, let's say, we could probe like right here, VBT plus. If you have to actually back probe it to get the reading, that's a scope. If you're just running off the scan tool, not so much. That's processed. That's highly processed information. Cool. So otherwise, I think, let me just make sure I don't have anything else super critical. There's just a lot of adjustments. So I do want to do a whole different lesson on Pico. And then just right here, these are the leads. So when we're back probing and stuff, the Pico has nice adapters, like this little needle back probing adapter can be really good. So super nice. And so again, if you get into this type of advanced diagnosis, you're going to spend thousands of dollars to be able to do this. Okay. It's just the way it is. All right. And overall, this is a little pocket one. You can buy these for $100 and they're not bad, but you can't send the file. You can't share the file. They could do one channel. If you have a one channel, you can measure one thing. If you have a multiple channel, you can be measuring multiple all at once. So like that picture way back here had like a whole bunch of different channels going. So like that one, you could measure multiple channels at once, or you could measure a whole bunch of different stuff just to maybe, for example, tell if the timing was right. So I think, and we'll go more into detail on this, but when we do the sensors, we'll apply these basic things, but we'll be specific on the wiring diagram later. All right. I think otherwise you guys are good. That's your electrical applied to engine performance.